Hello there, and welcome to Science for Sleep, where curiosity gets comfortable, questions stretch out like a cat in a warm patch of starlight, and the universe takes its time explaining itself. Tonight, we're going to wander gently toward the very centre of our galaxy, not in a rush, not with flashing alarms or dramatic countdowns, but with a slow, steady curiosity that's perfectly happy to drift along and see what appears along the way. Somewhere far beyond the soft glow of your screen, past the quiet hum of your room, past the familiar scatter of stars you might recognise in the night sky, there's a place where gravity gathers like a deep breath. A place where light hesitates, where matter swirls, and where time itself doesn't quite behave the way we're used to. This place has a name that sounds more like a constellation in an old storybook than a real location in space: Sagittarius A. It sits at the heart of the Milky Way, a supermassive black hole, calmly holding court in the middle of everything we call home. Before we drift too far into the cosmic deep, let me ask you something simple and human. Where are you listening from tonight? Is it late evening, early morning, or one of those quiet in-between moments when the world feels like it's holding its breath? Maybe you're wrapped in a blanket, maybe you're staring at the ceiling, or maybe your eyes are already starting to feel a little heavy. Wherever you are, whatever time it is for you, I'm glad you're here, sharing this little stretch of the universe with me. If you find this calm corner of science soothing, or if the idea of drifting through space in your imagination feels like a nice way to wind down, you might consider giving this video a like or subscribing. It helps this gentle exploration reach other curious minds who might be looking for a peaceful place to land at the end of their day. No pressure, of course. The universe isn't big on deadlines. Now, let's begin our slow journey inward. The Milky Way is a vast, spiralling city of stars. If you could float far above it and look down, you'd see long, glowing arms curling out from a bright central hub, like a cosmic pinwheel caught mid-spin. Inside those arms are hundreds of billions of stars, along with planets, clouds of gas, dust, and all the raw ingredients for future suns and worlds yet to be imagined. Our own solar system sits comfortably out in one of those arms, far from the bustling centre, like a quiet neighbourhood on the outskirts of a glowing galactic downtown. That central region, though, is anything but quiet. It's crowded, dense, and wrapped in thick clouds of dust that block visible light like heavy curtains drawn across a window. If you tried to look straight at the centre of the galaxy with your eyes or a regular telescope, you wouldn't see much more than a hazy glow. For a long time, that's exactly how it was for astronomers. They knew something important was there, something powerful, but it stayed hidden behind layers of cosmic fog. Over the decades, scientists began to notice something strange about the stars near the galactic centre. They weren't just drifting around peacefully, they were moving fast, incredibly fast. Some of them were whipping around an invisible point, tracing tight, looping paths through space as if they were tied to something massive at the centre by an unseen rope. By carefully tracking those motions, astronomers could do a kind of cosmic detective work. They could calculate how much mass must be sitting there to make stars move the way they do. The answer was staggering. At the heart of the Milky Way, in a region no larger than our solar system, there appeared to be something with the mass of about 4 million suns. But it wasn't shining, it wasn't glowing, it wasn't giving off the kind of light a star would. It was dark, dense, invisible. This was Sagittarius A, a supermassive black hole. Now, despite what movies and dramatic illustrations sometimes suggest, a black hole isn't a giant vacuum cleaner roaming through space, sucking up everything in its path. It's more like an object that sits there, quietly exerting an enormous gravitational pull on its surroundings. If you get too close, yes, things can fall in and never come back out. But from a safe distance, a black hole behaves much like any other massive object. Stars can orbit it, gas can swirl around it, Entire regions of space can exist in its gravitational grip without being instantly destroyed. For a long time, Sagittarius A was more of an idea than an image. Scientists had strong evidence it was there, and they could describe its mass, its location, and its influence, but actually seeing anything directly associated with it was another matter entirely. The centre of the galaxy is one of the most difficult places to observe. Dust blocks visible light. The region is crowded with stars, making it hard to pick out fine details, and the black hole itself doesn't emit light, which makes it, by definition, a challenging thing to photograph. This is where technology, patience, and a bit of human stubbornness come into the story. Over the years, astronomers developed new ways to look at the universe beyond the narrow band of light our eyes can see. They learned to observe in radio waves, infrared, ultraviolet, X-rays, and gamma rays. Each of these reveals a different version of the cosmos, like switching between filters on a camera. Infrared, in particular, turned out to be incredibly useful for peering through dust. While visible light gets scattered and absorbed by those thick clouds, infrared light can slip through more easily, carrying information from regions that would otherwise stay hidden. Even so, studying Sagittarius A remained a slow and careful process. Scientists watched stars orbit it over years and decades. They detected occasional bursts of energy as gas and dust heated up while spiraling inward. They built detailed models and simulations trying to understand what was happening in that crowded, energetic region at the core of our galaxy. Then, in the early 2020s, something new unfolded. High above Earth, far beyond the reach of our planet's atmosphere, a new telescope opened its golden eyes. The James Webb Space Telescope was designed to see the universe in a way no other telescope ever had before. It doesn't look at the sky in visible light the way the Hubble Space Telescope often does. Instead, Webb specializes in infrared. It's built to detect the faint heat signatures of distant galaxies, the soft glow of forming stars, and the subtle fingerprints of molecules in the atmospheres of planets orbiting other suns. Its mirror, made of 18 gold-coated segments, stretches over 6 meters across, giving it a light-gathering power that makes it one of the most sensitive space observatories ever launched. And it doesn't orbit Earth. It sits far out in space, about 1.5 million kilometers away, in a stable gravitational balance point known as Lagrange Point 2. There, it stays cold, shaded from the sun's heat, which is exactly what an infrared telescope needs to function properly. From that quiet vantage point, Webb began to send back images and data that quickly captured the world's attention. Nebulae glowing in rich, detailed colours, ancient galaxies from the early universe, their light stretched and softened by billions of years of cosmic expansion. Star-forming regions that looked less like fuzzy clouds and more like intricate three-dimensional landscapes, and eventually Webb turned its attention inward, toward the heart of our own galaxy. Sagittarius A had been studied before, but Webb offered something different. Its instruments could observe the region in multiple wavelengths of infrared light, allowing scientists to track changes over time and see how different types of energy move through the area. Instead of just taking a single snapshot, Webb could watch. It could monitor the subtle flickers, the gentle flares, and the shifting patterns of light that occur as material dances around the black hole. What it found wasn't a simple, static scene. The area around Sagittarius A turned out to be alive with motion and variation. Light didn't just glow steadily, it pulsed, it flared. It dimmed and brightened in ways that suggested complex ongoing processes. Gas and dust weren't drifting lazily. They were being heated, accelerated, and shaped by powerful magnetic fields and intense gravitational forces. One of the most intriguing discoveries was how often the region changed. Instead of occasional rare outbursts, Webb's observations revealed frequent smaller flares happening throughout the day. These weren't massive explosions visible across the galaxy. but subtle variations in brightness that hinted at constant activity near the edge of the black hole's influence. Imagine standing at the edge of a whirlpool in a river. The water near the centre moves differently than the water farther out. There are ripples, eddies, and sudden splashes as currents collide and swirl. Now replace the water with superheated gas and magnetic fields, and replace the whirlpool with a gravitational well so deep that even light struggles to escape. That's the kind of environment Webb was observing. Scientists began to piece together a picture of what might be causing these flickers. One leading idea involves magnetic reconnection. This is a process where twisted magnetic field lines suddenly snap and realign, releasing bursts of energy in the process. It's something we see on the Sun, where it can trigger solar flares. Near a black hole, where magnetic fields are intense and conditions are extreme, similar processes could be happening on a much more powerful scale. Another part of the puzzle comes from the disk of material that orbits Sagittarius A. While our galaxy's central black hole isn't currently devouring large amounts of matter, there is still gas and dust slowly circling it, forming what's known as an accretion flow. As this material spirals inward, it heats up and emits radiation. Changes in how that material moves, clumps, or interacts with magnetic fields can lead to the kind of brightness variations Webb detected. What made these findings especially interesting wasn't just that something was happening, but how often and how consistently it seemed to be happening. The centre of the Milky Way, it turns out, isn't a quiet, dormant place. It's more like a softly glowing, constantly shifting environment, where energy is being released in gentle, frequent pulses. For scientists, this raised new questions. How exactly is energy transported in this region? What role do magnetic fields play in shaping the behaviour of matter near the black hole? And how does Sagittarius A compare to the much more active supermassive black holes found in the centres of other galaxies, some of which shine brightly as quasars, visible across billions of light years? By studying our own galactic centre in such detail, astronomers have a kind of nearby laboratory for understanding these more distant, more extreme systems. Sagittarius A is relatively calm compared to those cosmic powerhouses, which makes it a useful reference point. It allows scientists to explore what a supermassive black hole looks like when it's not in a feeding frenzy, when it's in a quieter, more settled phase of its life. There's something quietly humbling about that idea. Right now, as you sit or lie wherever you are, surrounded by the small familiar details of your own world, there's a supermassive black hole 4 million times the mass of the Sun sitting at the centre of the galaxy. It's not making headlines. It's not tearing stars apart in dramatic fashion. It's simply there, influencing the motion of stars, shaping the structure of the Milky Way, and occasionally sending out soft, subtle signals that travel tens of thousands of light years before being caught by a telescope floating silently in space. Those signals began their journey long before any human built a mirror out of gold-coated segments or figured out how to send a machine to a gravitational balance point beyond the moon. They left the galactic centre when Earth was a very different place, and they arrived here just in time for us to notice them. As Webb continues to watch Sagittarius A, scientists are collecting more data, building longer timelines, and looking for patterns in the way the light changes. With every observation, they refine their models and test their theories, trying to understand how gravity, magnetism, and motion interact in one of the most extreme environments in our cosmic neighbourhood. And in a way, that slow, careful process mirrors what we're doing here. We're not racing to a conclusion. We're not trying to wrap everything up neatly. We're simply following a thread of curiosity, letting it lead us from the familiar world around us into a region of space where the rules we take for granted start to bend and blur. In the quiet glow of infrared light and the steady patience of a telescope a million kilometers from home, a story is unfolding about the heart of our galaxy. It's a story made of data points, theories, and long nights of observation. But it's also a story about how humans, small and temporary as we are, reach outward with questions and build tools to listen to the faint whispers of the universe. As we continue this gentle drift toward the deeper details of what Webb is seeing and what it might mean, let's carry that sense of slow wonder with us. There's no rush. The stars have been here for a long time, and Sagittarius A isn't going anywhere anytime soon. So take a slow breath, let your thoughts settle a little, and stay with me as we move closer to the strange glowing environment that surrounds the darkest object in our galaxy. There's more to notice in the subtle changes of light and motion, and we're only just beginning to trace their quiet patterns. If you were able to drift far beyond the gentle curve of Earth's atmosphere and keep going, past the familiar paths of satellites and the quiet watch of the moon, you would eventually find yourself in a place where the Milky Way reveals its true shape. From out there, our galaxy wouldn't look like a scattered band of light across a dark sky. It would appear as a vast, glowing spiral, its arms curling outward from a bright, crowded centre, like slow-moving streams of starlight frozen in motion. That centre, dense and luminous, would draw your attention almost immediately, not because it shines the brightest, but because it holds the greatest weight. Our home in the galaxy is comfortably distant from this region. We sit in one of the spiral arms far enough away that the night sky feels spacious, orderly, and calm. The stars around us drift in wide, gentle orbits, and the rhythms of the cosmos unfold at a pace that feels almost leisurely. But the closer you move toward the galactic centre, the more everything changes. Space becomes crowded. Stars cluster together in thick swarms. Clouds of gas and dust pile up, glowing faintly with heat and energy. The entire region feels compressed, as though gravity itself is drawing the universe inward, inviting everything to lean closer. At the very heart of this cosmic gathering place lies something you cannot see with your eyes, something that does not glow or sparkle or cast shadows in the usual way. Instead, it reveals itself through its influence, through the way everything around it behaves. This is Sagittarius A, the dark heart at the centre of our galaxy, a supermassive black hole quietly shaping the motion of stars, gas and dust across tens of thousands of light years. For most of human history, this hidden centre was nothing more than a mysterious idea. People looked up at the Milky Way as a bright milky band stretching across the sky and told stories about rivers, roads, and celestial animals woven into its light. The notion that there was a single, powerful object anchoring all of it would have seemed like a piece of cosmic mythology. Even when telescopes became powerful enough to map stars in detail, the galactic centre remained stubbornly elusive. Thick clouds of dust blocked visible light, hiding whatever lay behind them like curtains drawn across a brightly lit room. It wasn't until astronomers began looking beyond visible light that the first clues started to emerge. Radio telescopes, which detect long wavelengths of electromagnetic radiation, were able to peer through the dust and pick up signals from the galactic centre. In the 1970s, scientists identified a compact, bright source of radio waves coming from that region. They named it Sagittarius A, after the constellation Sagittarius, which marks the direction of the galactic centre in the sky. Within that source, they later identified an even more concentrated point of emission, and that's where the star was added. Sagittarius A. At first, it was just a bright spot on a radio map. Interesting, but not yet extraordinary. What transformed it from a curious feature into something truly profound was the movement of the stars around it. Over the years, astronomers used increasingly precise infrared telescopes to track individual stars in the crowded region near the galactic centre. They watched how these stars moved, not just in a general sense, but in fine detail, charting their paths across the sky year after year. Some of these stars followed wide, gentle orbits, but others moved in tight, fast loops around a single invisible point. One star in particular, known as S2, became famous among astronomers. It completes a full orbit around Sagittarius A in just about 16 years. For comparison, Our Sun takes roughly 225 million years to make one full trip around the centre of the galaxy. S2, by contrast, is racing around its path at incredible speeds, especially when it swings close to the central object. At its fastest, it moves at thousands of kilometers per second, a significant fraction of the speed of light. By applying the laws of gravity and motion, scientists could use S2's orbit like a measuring tape. The tighter and faster an object orbits, the more mass must be pulling on it. When they did the calculations, the results pointed to something with the mass of about 4 million suns, squeezed into a region of space no larger than our solar system. There are very few things in the universe that can pack that much mass into such a small volume. A cluster of stars wouldn't work. It would quickly collapse or scatter. A dense cloud of gas would glow brightly as it heated up. The only explanation that fit both the mass and the darkness was a black hole. This realization changed the way we think about our place in the galaxy. We don't just live in a spiral of stars. We live in a structure that is, at its core, shaped by one of the most extreme objects nature can produce. Sagittarius A isn't an active, blazing monster like the supermassive black holes at the centres of some distant galaxies, which shoot out enormous jets of energy and shine across the universe as quasars. Ours is relatively quiet. Astronomers sometimes describe it as underfed. It isn't currently consuming large amounts of material, so it doesn't put on a dramatic show. But quiet doesn't mean insignificant. The gravitational influence of Sagittarius A extends far beyond its immediate surroundings. It plays a role in organising the motion of stars in the central region of the galaxy. It helps define the overall structure of the Milky Way, anchoring its spiral arms and contributing to the balance of forces that keep the galaxy stable over billions of years. To understand what this dark heart is really like, it helps to picture what a black hole actually is, beyond the popular images of swirling voids and cosmic vacuum cleaners. A black hole forms when a large amount of mass collapses into a very small space. For stellar mass black holes, this happens when a massive star runs out of fuel and its core collapses under its own gravity. Supermassive black holes like Sagittarius A's likely formed through more complex processes, involving the growth and merging of smaller black holes and the accumulation of vast amounts of gas and dust in the early universe. At the centre of a black hole is what physicists call a singularity, a point where, according to our current theories, density becomes infinite and the laws of physics as we know them break down. Surrounding that singularity is the event horizon, an invisible boundary. Once something crosses that boundary, it cannot escape, not even light. From the outside, you can never see what happens beyond it. All you can observe is the behaviour of things approaching it. Around Sagittarius A, there is a region filled with hot gas, dust and magnetic fields. This material doesn't fall straight in. Instead, it tends to spiral, forming a swirling flow known as an accretion disk, or, in the case of our relatively calm black hole, a more diffuse accretion structure. As this material moves, it heats up and emits radiation, especially in infrared and X-ray wavelengths. That faint glow is one of the main ways astronomers study the black hole's immediate environment. What makes the centre of the Milky Way especially fascinating is how much is happening in a relatively small volume of space. In the region surrounding Sagittarius A, stars are packed much closer together than they are in our local neighbourhood. Some of them are massive, young and bright, burning through their fuel quickly and living short, energetic lives. Others are older and quieter, drifting along in the complex gravitational dance of the galactic core. There are also enormous clouds of gas and dust, some of which are collapsing to form new stars, while others are being stretched and shaped by the gravitational forces at play. It's a place of both creation and destruction, of beginnings and endings happening side by side. For a long time, much of this activity was hidden from view. The dust that blocks visible light made it difficult to map the region in detail. But with the development of infrared astronomy, and especially with the arrival of instruments like the James Webb Space Telescope, scientists have been able to peel back those layers and see the galactic centre in a new way. Infrared light, which is essentially heat radiation, can pass through dust more easily than visible light. This allows telescopes like Webb to detect the warm glow of stars and gas that would otherwise remain concealed. It's like switching from a regular flashlight to a thermal camera and suddenly being able to see shapes and movements in the dark. As observations have become more detailed, the picture of the galactic centre has grown richer and more complex. Instead of a simple, empty region with a black hole at its core, scientists now see a dynamic environment filled with streams of gas, clusters of stars, and intricate structures shaped by gravity and magnetism. One particularly interesting feature is a ring of dense gas and dust known as the circumnuclear disk. This structure orbits the central region and acts as a kind of reservoir of material that can, under the right conditions, feed the black hole or contribute to new star formation. The balance between these processes, between material falling inward and material forming outward, is one of the key questions researchers are trying to answer. There's also evidence of past activity. While Sagittarius A is relatively quiet now, it may not always have been. Observations of large, bubble-like structures extending above and below the plane of the galaxy, known as the Fermi bubbles, suggest that the black hole might have been more active millions of years ago, releasing energy that shaped the surrounding space. These features hint at a history of cycles, periods of calm followed by bursts of activity, like a cosmic heartbeat playing out over geological timescales. Thinking about that can make time feel a little different. The light that astronomers observe from the galactic centre doesn't arrive instantly. It takes about 26,000 years to travel from Sagittarius A to Earth. That means when we look at the heart of the Milky Way, we're seeing it as it was 26,000 years ago, when humans on this planet were living in a very different world. There were no cities, no written languages, no telescopes pointed skyward, and yet the signals from that distant region were already on their way, crossing the vastness of space, long before anyone here could imagine what they might reveal. This sense of delayed connection is part of what makes studying the galactic centre feel so quietly profound. Every observation is a message from the deep past, a glimpse into a place that exists right now, but as it was long ago. It's a reminder that space and time are woven together in ways that stretch our everyday intuitions. Despite all the progress, there are still many mysteries surrounding Sagittarius A. Scientists want to know how exactly it interacts with its environment, how material moves and changes as it approaches the event horizon, and what role the black hole plays in the long-term evolution of the galaxy. They also want to understand how typical our situation is. Do most galaxies have similar quiet black holes at their centres? Or is the Milky Way unusual in some way? To answer these questions, researchers combine observations from many different instruments, each providing a piece of the puzzle. Radio telescopes map large-scale structures and jets. Infrared telescopes reveal stars and warm gas hidden behind dust. X-ray observatories detect high-energy events near the black hole itself. Together, these views create a layered picture, like looking at the same landscape through different kinds of light. What makes this process especially fitting for a place called a dark heart is that it's not about a single dramatic image. It's about patterns over time. It's about small changes in brightness, slight shifts in motion, and subtle variations in energy that, when carefully tracked and analysed, reveal the presence and behaviour of something we can never see directly. There's a certain quiet elegance to that. Instead of confronting the black hole head-on, scientists listen to its effects, like hearing footsteps in another room, or watching ripples spread across a pond after a stone has been dropped. From where you are now, in a room with walls, a ceiling, and the familiar gravity of Earth holding you gently in place, it might be hard to fully picture a region of space where gravity is so strong that it can bend the path of light and stretch the flow of time. But in a sense, you're already connected to it. Every atom in your body was forged in stars that were born, lived and died within this galaxy, under the long-term influence of its central mass. Sagittarius A is part of the story of how the Milky Way came to be, and by extension part of the story of how we came to be here, able to wonder about it. As observations continue and new data comes in, the dark heart of our galaxy becomes a little less mysterious, not because it's fully revealed, but because we're learning how to read its quiet signals more clearly. Each flicker of light, each shifting star, each subtle change in the glow of gas adds another line to a story that's still being written. And while it might be tempting to think of this as a distant, abstract subject, something far removed from daily life, there's a gentle connection worth holding on to. The same physical laws that govern the motion of stars around a supermassive black hole also govern the motion of your own breath as it rises and falls, the way warmth moves through your hands, and the steady pull of gravity that keeps you comfortably anchored to the ground. In both cases, it's about forces, motion, and the quiet persistence of change over time. For a long time, Sagittarius A felt like one of those cosmic characters that scientists thought they had figured out, at least in broad strokes. Not fully understood, not completely mapped, but familiar in the way a distant mountain becomes familiar. You know its shape on the horizon. You know where it rises and sets. You can describe it, even if you've never climbed it. The black hole at the centre of the Milky Way was, in many ways, like that. A massive object, 4 million times the mass of the Sun, sitting quietly at the galactic core, pulling on nearby stars, occasionally flaring when a bit of gas wandered too close. A supermassive black hole, yes, but a calm one. A predictable one, almost polite as black holes go. That sense of familiarity didn't come from a single discovery. It grew slowly, built from decades of patient observation, careful measurement, and the steady layering of evidence. Astronomers tracked stars, mapped radio signals, and watched faint glows of energy appear and fade near the galactic centre. Over time, a kind of working personality for Sagittarius A emerged. It wasn't a ravenous monster, it wasn't a blazing quasar, it was more like a quiet anchor, a heavy presence that shaped its surroundings without constantly drawing attention to itself. In that picture, Sagittarius A became a useful reference point. If you wanted to understand how black holes behaved when they weren't actively devouring large amounts of matter, this was your example. It allowed scientists to study a supermassive black hole in a relatively low-energy state, a kind of cosmic resting phase. Compared to the brilliant, violent centres of some distant galaxies, ours seemed almost peaceful. But peaceful in astronomy is always a relative term. Even in its calmer moments, the region around Sagittarius A is anything but simple. It's filled with hot gas, tangled magnetic fields, and stars moving at astonishing speeds. Yet, for a long time, the general idea held. There was a central black hole, a surrounding environment, and a set of physical rules that governed how matter and energy moved through that space. Models were built, simulations were run, textbooks were written. The black hole at the heart of the Milky Way took its place as a kind of well-behaved example in the broader family of these extreme objects. One of the most powerful tools scientists used to shape this understanding was motion. By watching how stars moved, they could infer the presence, mass, and location of the invisible object they were orbiting. The orbits of stars like S2 weren't just interesting, they were precise tests of gravity itself. When S2 swooped close to Sagittarius A, its path showed tiny deviations that matched the predictions of Einstein's theory of general relativity. Space and time themselves were being slightly warped by the black hole's immense mass, and the star's motion traced out those subtle curves. This was a remarkable confirmation. Not only was there a supermassive black hole at the centre of the galaxy, but it behaved, at least in these respects, exactly as the theory said it should. Gravity followed the rules. Orbits made sense. The universe, at least here, seemed to be keeping its promises. Beyond the stars there was the matter that drifted closer in. Gas clouds, dust, and stray particles formed a loose, swirling structure around the black hole. As this material moved inward, it heated up and emitted radiation. Astronomers could detect this radiation, especially in radio waves, infrared light, and X-rays. The brightness of Sagittarius A in these wavelengths varied over time, but mostly in ways that could be explained by changes in how much material was flowing toward it, or how that material was interacting with magnetic fields. The idea of accretion, the slow feeding of a black hole, became central to this picture. In more active galaxies, accretion disks shine brilliantly as enormous amounts of matter fall inward, releasing vast quantities of energy. In our galaxy, the accretion flow around Sagittarius A seemed thin and inefficient. Most of the material didn't make it all the way in. It swirled, heated up, and then often got pushed back out by winds and magnetic forces. This made Sagittarius A something of a puzzle, but a comfortable one. It fit into a category. It was a low-luminosity active galactic nucleus, a supermassive black hole that was technically active, but only just. It offered a chance to study what black holes look like when they're not in their dramatic high-energy phases. Then, in 2022, something quietly significant happened. The Event Horizon Telescope, a global network of radio observatories working together as one Earth-sized instrument, released the first ever image of Sagittarius AR. It wasn't a photograph in the traditional sense, but a reconstructed image based on radio data collected from telescopes around the world. What it showed was a glowing ring of light surrounding a dark centre, the shadow of the black hole. For the first time, humanity had a visual representation of the object that had been shaping our galaxy from the shadows. The image was fuzzy, soft around the edges, but unmistakable. It matched the predictions of general relativity. The size of the shadow fit the mass estimates. The shape aligned with the idea of light being bent around an event horizon. It was a moment of quiet validation. Here was Sagittarius A behaving just as expected. The black hole we thought we knew looked, in its own subtle way, exactly like it was supposed to. The models held. The theories stood firm. The mountain on the horizon had been sketched, and the sketch matched the landscape. But even as that image settled into the collective imagination, scientists knew it was only part of the story. The Event Horizon Telescope gave a snapshot, a kind of cosmic portrait. It didn't show motion, change, or the full range of activity in the surrounding region. For that, other instruments working in different wavelengths of light were needed, and that's where things began to feel a little less settled. Before the arrival of more advanced infrared observations, much of what scientists knew about Sagittarius AE came from long-term averages. They could say how bright it usually was. They could describe typical flare rates. They could outline the general structure of the environment. But fine details, especially those that changed on short timescales, were harder to capture. Some telescopes did detect flares, bursts of energy that appeared suddenly and then faded. These were often explained as clumps of gas or dust heating up as they moved close to the black hole, or as magnetic fields releasing stored energy. The events were interesting, but they didn't seem to challenge the overall picture. They fit within the expected range of behaviour for a relatively quiet supermassive black hole. The mental image of Sagittarius A remained stable, a heavy dark centre, a thin, swirling environment, occasional flickers of activity, a steady, gravitational presence shaping the heart of the Milky Way. What made this image so appealing was its simplicity. In a universe filled with complexity, here was something that could be described with a clear set of principles. Gravity pulls, matter spirals, energy is released, space and time bend. The story had a rhythm to it, a kind of logical flow that made it feel almost approachable, despite the extreme nature of the object at its centre. This didn't mean there were no unanswered questions. There were many. How exactly does material move in the chaotic region near the event horizon? What role do magnetic fields play in shaping that motion? How does the black hole interact with the surrounding stars and gas on longer timescales? But these were framed as refinements, as details to be filled in, not as challenges to the core idea. Sagittarius A was, in a sense, behaving itself. There was also a comforting comparison at work. When astronomers looked at distant galaxies with blazing active centres, they saw black holes that were anything but calm. These objects were surrounded by thick, luminous accretion disks. They shot out jets of particles that stretched across intergalactic space. They outshone entire galaxies. Against that dramatic backdrop, our own black hole felt modest. It was like comparing a quiet fireplace to a raging bonfire. Both are fire, both follow the same basic rules, but one is content to glow softly while the other demands attention from miles away. This comparison helped place Sagittarius A in a broader cosmic context. It suggested that black holes go through phases. Sometimes they're active, feeding heavily, shaping their galaxies in dramatic ways. At other times they're subdued, quietly existing as massive anchors in the centres of star systems. The Milky Way, it seemed, was in one of those quieter chapters. As researchers refined their models, they began to treat Sagittarius A as a kind of baseline. If you wanted to test a theory about how black holes behaved at low accretion rates, this was your case study. Observations were compared to simulations. Small discrepancies were noted and adjusted for. Over time, the match between theory and observation grew tighter. There was a sense, not of completion, but of confidence. And yet confidence in science is often a temporary thing. It's not a declaration that the story is finished. It's more like a signpost that says, this is what we understand so far. Beyond that signpost, there's always more road. One of the subtle challenges in studying Sagittarius A is the sheer scale of time involved. Changes in the environment around a black hole can happen quickly on human timescales, but the larger story unfolds over thousands, millions, and even billions of years. The Milky Way itself has been evolving for more than 13 billion years, shaped by mergers, star formation, and the slow migration of matter through its spiral arms. Sagittarius A has been part of that process from very early on. It likely grew along with the galaxy, accumulating mass as stars formed and died, as gas clouds collapsed and drifted inward, and as smaller black holes merged into larger ones. The quiet phase we see now is just a snapshot in a much longer narrative. This long view made it tempting to think of the black hole as a kind of constant, a stable feature in a changing galaxy. Stars come and go. Clouds form and disperse. But the black hole remains, a dark, enduring presence at the centre. Even that idea, though, is a simplification. On shorter timescales, the region around Sagittarius A is lively and variable. The gas and dust don't move in smooth, perfect circles. They follow turbulent paths influenced by shocks, collisions, and shifting magnetic fields. Stars pass close by, their gravity stirring the environment as they go. Occasionally, a clump of material ventures too near and gets heated, stretched, and torn apart, adding a brief flash of energy to the scene. These details were always part of the scientific picture, but they lived mostly in the realm of models and indirect measurements. They were inferred, not watched in real time. The black hole we thought we knew was in a sense a carefully averaged version of the real thing, a portrait painted with broad strokes, smoothed over by years of data combined into a single coherent image. What would happen, scientists wondered, if we could watch more closely? If we could see not just the average behaviour, but the moment-to-moment changes? If we could track the flickers and flares as they happened, rather than piecing them together after the fact? Those questions lingered in the background, waiting for the right tools. From your perspective here on Earth, it might feel like a distant, abstract concern. After all, Sagittarius A is 26,000 light-years away. Whatever it's doing now won't be visible to us for tens of thousands of years. The idea that its behaviour could matter to us on a personal level might seem like a stretch. But there's a quiet connection worth noticing. The way scientists approach this black hole, building models, testing them, refining them, and then revisiting their assumptions when new data arrives, mirrors a broader pattern in how we try to understand the world. We build mental pictures of how things work, we grow comfortable with them, and then occasionally something comes along that nudges us to look again, to adjust the edges of that picture, or sometimes to redraw it entirely. Sagittarius A had settled into its role as the familiar quiet giant at the centre of the Milky Way. The black hole we thought we knew was well behaved, predictable, and, in a strange way, reassuring. It fit neatly into the larger story of galaxies and their evolution. But the universe has a habit of offering small surprises rather than big announcements. It doesn't usually shout, "You're wrong." It whispers, "There's more here than you thought." As new instruments began to watch the galactic centre with greater sensitivity and finer resolution, those whispers started to become a little more noticeable. Subtle changes in light, patterns that didn't quite match the smooth curves of the models, variations that suggested a level of activity and complexity that hadn't been fully appreciated before. The black hole itself didn't change. Its mass didn't suddenly shift. Its event horizon didn't move. What changed was our view of the environment around it, the delicate dynamic region where gravity, magnetism and motion meet. And that's where the familiar picture began to soften at the edges. So as we sit with this idea of a black hole that seemed well understood, almost comfortable in its cosmic role, it's worth holding a little space for curiosity. Not the dramatic, breathless kind, but the quiet kind that's willing to notice small differences and follow them patiently. Because the story of Sagittarius A isn't just about a massive object at the centre of the galaxy. It's about how our understanding of it evolves, how new ways of seeing can turn a familiar landmark into something freshly intriguing. Trying to look at the centre of the Milky Way is a bit like standing in the middle of a crowded room and attempting to spot a single candle on the far wall, while everyone else is carrying a flashlight, and someone has decided to fill the air with a gentle but persistent fog. The candle is there. You know it's there. You can even see a soft glow in its general direction. But the path between you and that small, steady light is busy, cluttered, and full of things that bend, scatter, and block what you're trying to see. From our place inside the galaxy, the challenge begins with something very simple. We're not looking at the Milky Way from the outside. We are part of it. Our solar system sits embedded in one of the spiral arms, surrounded by stars, clouds of gas and dust. When we look toward the centre, we're peering through the thickest, most crowded part of the galactic disk. Every photon of light that tries to reach us from that distant region has to pass through layer after layer of cosmic material. This material, especially dust, is one of the main reasons the galactic centre stayed hidden for so long. Cosmic dust is not like the dust that settles on a shelf in your room. It's made of tiny solid particles, often smaller than a grain of smoke, composed of elements like carbon, silicon, and oxygen. These particles are scattered throughout the galaxy, mixed in with clouds of gas. They might sound insignificant on their own, but over thousands of light years they add up to a serious obstacle for light trying to travel through. Visible light, the kind our eyes and traditional telescopes use, is particularly vulnerable to this dust. When it hits those tiny particles, it gets absorbed or scattered in different directions. The result is a dimming and reddening of the light, a bit like how the sun looks redder and softer when it's low on the horizon, and its light has to pass through more of Earth's atmosphere. In the direction of the galactic centre, the amount of dust is so high that visible light is almost completely blocked. If you point an optical telescope straight towards Sagittarius A, you won't see a black hole, or even the stars orbiting near it. You'll see a dark patch, broken by a few foreground stars that happen to be much closer to us. For a long time, this made the centre of the Milky Way feel like a blank spot on the map. But dust isn't the only complication. The region around the galactic centre is also one of the most crowded parts of the galaxy. Stars there are packed much more tightly than in our local neighbourhood. In some areas, the density can be millions of times higher than what we experience near the Sun. This creates a visual problem even for wavelengths of light that can get through the dust. Imagine trying to pick out a single person in a massive crowd, where everyone is wearing similar colours and moving in different directions. The light from all those stars overlaps, blurs together, and competes for attention. Separating one object from another requires incredibly sharp resolution and precise measurements. Then there's the issue of distance. Sagittarius A is about 26,000 light-years away. That's a number that's easy to say and hard to feel. Light from the galactic centre began its journey toward us long before modern humans existed. Over that vast distance, even something large can appear very small. From Earth, the region around the black hole spans a tiny angle in the sky, smaller than a grain of sand held at arm's length. To see fine details at that scale, astronomers need instruments with extraordinary precision. Earth's atmosphere, helpful as it is for keeping us alive, is not particularly friendly to astronomy. The air above us is constantly moving, creating turbulence that blurs incoming light. This is why stars appear to twinkle. It's charming to look at, but it's a problem if you're trying to measure the exact position of a star or track its motion over time. For observations of the galactic centre, this atmospheric distortion can smear out the already faint and crowded signals, making it even harder to separate one star from another or detect subtle changes in brightness. Over the years, astronomers have developed techniques to deal with this. One of the most important is adaptive optics. This involves using a flexible mirror in a telescope that can change its shape in real time to counteract the distortions caused by the atmosphere. By measuring how the incoming light is being warped, often using a reference star or a laser-generated artificial star, the system can adjust the mirror hundreds of times per second to sharpen the image. Even with adaptive optics, though, there are limits to what ground-based telescopes can do. Some wavelengths of light are absorbed by Earth's atmosphere before they ever reach the ground. Infrared light, in particular, is partially blocked by water vapour and other gases in the air. To get the clearest view in these wavelengths, it helps to go above the atmosphere entirely. That's one of the reasons space telescopes like the James Webb Space Telescope are so valuable for studying the galactic centre. But before we drift too far into the tools themselves, it's worth lingering on the nature of the environment we're trying to observe. The region around Sagittarius A is not just crowded and dusty, it's also active. Gas clouds collide, shock waves ripple through the medium, magnetic fields twist and stretch, stars move at high speeds, sometimes interacting with the surrounding material in ways that produce bursts of radiation. This means the scene is not static. It changes over time, sometimes on timescales of minutes or hours, sometimes over years or decades. Capturing a clear picture is not just about taking a sharp image, it's about monitoring how things evolve. This adds another layer of difficulty. If you take a snapshot at one moment, you might catch a flare or a bright spot that fades away shortly after. Another snapshot taken later might show a different pattern. To understand what's really going on, scientists need long-term observations, repeated over and over, to distinguish between fleeting events and persistent structures. There's also the challenge of working across different types of light. The galactic centre emits radiation across the entire electromagnetic spectrum, from long wavelength radio waves to high-energy X-rays and gamma rays. Each of these carries different information about the physical processes at work. Radio waves can trace large-scale structures and cool gas. Infrared light reveals stars and warm dust. X-rays often point to extremely energetic events near the black hole itself. No single telescope can observe all of these at once. Instead, astronomers have to combine data from many instruments, often taken at different times and with different resolutions. This process is a bit like trying to assemble a single coherent picture from a stack of photographs taken with different cameras, under different lighting conditions and at different moments. Aligning these views requires careful calibration and a deep understanding of how each instrument works. Then there's the issue of scale. Some of the most interesting features near Sagittarius A are very small, at least in angular terms. The region where gravity becomes so strong that it dramatically affects the path of light is tiny when seen from Earth. To resolve features at that scale, astronomers need techniques that go beyond the capabilities of a single telescope. This is where ideas like interferometry come in. By linking multiple telescopes together and combining their signals, scientists can effectively create a much larger, virtual telescope. The Event Horizon Telescope, which produced the first image of Sagittarius A, uses this technique. It connects radio observatories across the globe from Hawaii to Spain to Antarctica, synchronizing them with atomic clocks so that they can work together as if they were parts of one Earth-sized instrument. But interferometry brings its own challenges. The data from each telescope has to be precisely timed, calibrated, and combined. Even tiny errors can blur the final image. Weather, equipment issues, and atmospheric conditions at each site can affect the quality of the data. Producing a single image can take years of observation and analysis, and that's just for radio wavelengths. Infrared observations, like those made by Webb, face a different set of hurdles. Infrared light is essentially heat. This means that anything warm can interfere with the signal. Telescopes themselves emit infrared radiation. So does Earth. So does the Sun. To detect the faint infrared glow from distant stars and gas near the galactic center, the telescope has to be kept extremely cold. That's why Webb has a massive sunshield, about the size of a tennis court, which blocks heat from the Sun, Earth, and Moon. It allows the telescope to cool down to temperatures where its own heat doesn't overwhelm the signals it's trying to detect. Even with this cooling, the instruments have to be carefully designed and calibrated to distinguish between real astronomical signals and background noise. Another subtle difficulty comes from motion. The Earth is rotating. It's orbiting the Sun. The Sun is moving through the galaxy. The galaxy itself is drifting through space relative to other galaxies. All of this motion affects how we observe distant objects. Light can be shifted slightly in wavelength, a phenomenon known as the Doppler effect. Positions can appear to change over time due to parallax and proper motion. When astronomers track the motion of stars near Sagittarius A, they have to account for all of these factors. The apparent movement they see on the sky is a combination of the star's true orbit around the black hole and the motion of the observer. This requires careful modelling and precise measurements over long periods. A small error in accounting for Earth's motion or the telescope's position can lead to incorrect conclusions about how a star is moving. There's also the matter of time delays. Because the galactic centre is so far away, the light we see left there tens of thousands of years ago. When we observe a change, like a flare or a brightening, we're seeing an event that happened in the distant past. This doesn't change the physics, but it does add a philosophical layer to the work. We're piecing together a story about a place that exists now, but as it was long ago. From a practical standpoint, this means that when scientists talk about what Sagittarius A is doing, they're really talking about what it was doing 26,000 years in the past. The region might be different now, or it might be very similar. We won't know for a long time. Despite all these challenges, progress has been steady. Each new generation of telescopes has peeled back another layer of difficulty. Infrared detectors have become more sensitive. Adaptive optics have become more precise. Data processing techniques have grown more powerful. Space-based observatories have eliminated the blurring effects of the atmosphere. With each improvement, the galactic center has come into slightly sharper focus. But there's an interesting side effect to this increased clarity. The more closely scientists look, the more complexity they see. Features that once appeared smooth and simple turn out to be structured and variable. Regions that seemed quiet reveal subtle motions and changes. This can make the job feel like it's getting harder rather than easier. There's also the human side of the challenge. Studying the galactic center requires long-term commitment. Tracking stellar orbits takes decades. Building and launching a space telescope can take a generation of scientists. Analysing data from a global network of observatories involves teams spread across continents, working together over years. This kind of work doesn't fit neatly into short time frames. It asks for patience, collaboration, and a willingness to accept that some answers will come slowly, if at all. In a way, this mirrors the nature of the object being studied. A supermassive black hole is not something that changes dramatically from day to day. Its influence unfolds over immense spans of time. Understanding it means aligning human timescales, which are measured in years and careers, with cosmic timescales, which are measured in millions and billions of years. From where you are now, the idea of waiting decades to see a single star complete an orbit might sound abstract. But for astronomers, that's part of the rhythm of the work. Observations made by one generation are often analysed and interpreted by the next. Data collected today might not reveal its full significance until new theories or tools emerge years down the line. All of this makes looking at the galactic centre a kind of layered challenge. There's the physical layer, with dust, distance, and crowded stars blocking and blending the light. There's the technical layer, with telescopes, detectors, and data processing systems pushing the limits of what's possible. There's the conceptual layer, where models and theories have to be refined to match increasingly detailed observations. And there's the human layer, where time, collaboration, and curiosity shape the pace of discovery. What makes this especially fitting for a place called a dark heart is that it's not just hidden by one thing, it's hidden by many, and each one requires a different approach to overcome. Yet despite all of this, we keep finding ways to look. We build mirrors out of gold-coated segments and send them 1,000,000 kilometers into space. We link radio dishes across the planet and synchronize them with atomic clocks. We write algorithms that sift through mountains of data, searching for patterns too subtle for the eye to notice. Each of these efforts is, in its own way, a response to the same simple desire: to see what's there, to understand what's shaping the galaxy we live in. As these tools come online and observations grow more detailed, the view of the galactic centre becomes less like a distant, blurry glow and more like a living environment, full of motion and structure. But with that clarity comes new questions. Why does the light flicker the way it does? How do magnetic fields shape the flow of gas? What determines when material falls inward and when it gets pushed away? These questions don't arise in spite of the difficulty of looking. They arise because of it. Each layer of challenge that gets peeled back reveals another layer of complexity beneath. So, when you hear about new images or data from the heart of the Milky Way, it's worth remembering how much effort lies behind each pixel and each measurement. What looks like a soft glow or a faint ring of light represents years of work, countless calculations, and a chain of technology stretching from a quiet control room on Earth to a silent instrument floating in the cold of space. In the gentle pause between one observation and the next, there's a kind of connection worth noticing. The same patience it takes to study something so distant and hidden is the same patience it takes to sit quietly and let your own thoughts settle. Both involve waiting for subtle changes, for small signals, for moments of clarity that don't announce themselves loudly. Long before the James Webb Space Telescope ever unfolded its golden mirrors in the quiet cold of space, it existed as an idea, a kind of shared wish among scientists who wanted to see the universe in a way that simply wasn't possible yet. The Hubble Space Telescope had given humanity breathtaking views of galaxies, nebulae, and distant stars, and it had reshaped how we picture the cosmos. But even as Hubble was still delivering its steady stream of images, astronomers were already thinking about what lay beyond its reach. They knew there were parts of the universe that glowed too softly, too faintly, or in the wrong kind of light for Hubble to truly reveal. The universe, as it turns out, does not tell all its stories in the bright familiar colours we see with our eyes. A great deal of what happens in space is written in infrared light. This is the kind of light we associate with warmth, the gentle heat you feel from a cup of tea or a patch of sunlight on the floor. In cosmic terms, infrared light comes from cool stars, warm dust, and distant galaxies whose light has been stretched and softened by billions of years of cosmic expansion. It also comes from regions hidden behind thick veils of dust, where visible light simply cannot pass. If you want to look into the heart of a star-forming cloud, or peer through the dusty disk of the Milky Way toward its crowded centre, infrared is the language you need to speak. That realization set the stage for a telescope unlike any that had come before. The James Webb Space Telescope, often just called Webb, was designed to be a kind of time machine, and a dust-piercing eye rolled into one. It would look back toward the earliest galaxies that formed after the Big Bang, and it would look inward toward regions of space that had always been hidden behind cosmic curtains. It would study the birth of stars, the chemistry of distant planets, and the faint glow of galaxies so far away that their light began its journey before Earth itself had formed. But to do all of that, Webb needed to be something very different from Hubble. Hubble orbits Earth, circling our planet every 90 minutes or so. It sees invisible and ultraviolet light, along with a bit of infrared. Webb, on the other hand, was designed to focus almost entirely on infrared, and that choice shaped nearly every aspect of its design. Infrared astronomy comes with a unique challenge. Because infrared light is essentially heat, anything warm can interfere with the signal. A telescope that's too warm will glow in infrared, and that glow can drown out the faint light coming from distant objects. So, Webb had to be cold, very cold. This requirement alone meant that Webb couldn't stay in a low Earth orbit like Hubble. The Earth, the Moon, and the Sun would constantly warm it, making it difficult to keep the instruments at the low temperatures they needed. Instead, Webb was sent far out into space, to a location known as the Second Lagrange Point, or L2. This is a place where the gravitational pull of the Earth and the Sun balance in just the right way to allow a spacecraft to orbit the Sun along with Earth, maintaining a relatively stable position. At L2, about 1.5 million kilometers from Earth, Webb could keep the Sun, Earth and Moon all on the same side of the telescope. That made it possible to block their heat with a single, massive sun shield, leaving the telescope itself in permanent shadow. The sun shield is one of Webb's most striking features, even if it doesn't show up in the images the telescope takes. It's made of 5 layers of a thin reflective material called capton, each layer separated by a small gap. Together, these layers reduce the heat from the sun by a factor of more than 1 million. On the sun-facing side, temperatures can reach well over 100 degrees Celsius. On the telescope side, where the mirrors and instruments sit, temperatures drop to around minus 230 degrees Celsius. This dramatic temperature difference exists across a structure that's only a few meters thick. When Webb launched, it didn't look like the telescope we see in diagrams and photographs today. It was folded up, compacted to fit inside the nose of a rocket. Over the course of several weeks after launch, it went through a carefully choreographed unfolding process. The sun shield deployed layer by layer. The mirror segments swung out into place, antennas extended. Each step had to work perfectly. There were no astronauts waiting nearby with a toolbox. If something failed, there would be no easy way to fix it. That period of deployment was, for many people, a quiet kind of suspense. Not the loud, dramatic kind, but the slow, careful kind, where every small success is followed by a pause, a check, and then the next step. When Webb finally settled into its operational configuration and began cooling down, it felt less like a single moment of triumph and more like the gentle exhale after a long, careful breath. At the heart of Webb is its mirror. Instead of a single, solid piece of glass, Webb's primary mirror is made up of 18 hexagonal segments, each coated with a thin layer of gold. Gold is excellent at reflecting infrared light, which makes it ideal for Webb's purposes. When these segments are aligned, they form a mirror more than 6 meters across. That's more than twice the diameter of Hubble's mirror. This larger mirror gives Webb a huge advantage. The bigger the mirror, the more light it can collect. And when you're trying to detect faint signals from distant galaxies or subtle glows from dust near a black hole, every extra photon matters. Aligning those 18 segments was another delicate process. After deployment, engineers and scientists had to carefully adjust each piece, using tiny motors to shift them by fractions of a human hair, until they all acted as a single, smooth surface. This process took months, and it relied on detailed measurements and patient fine-tuning. Once the mirror was aligned and the instruments were cooled and calibrated, Webb was ready to begin its work. It carries 4 main scientific instruments, each designed to look at the universe in a slightly different way. There's NIRCam, the near-infrared camera, which takes images of stars, galaxies and nebulae. There's NIRSpec, the near-infrared spectrograph, which breaks light into its component wavelengths, allowing scientists to analyze the chemical makeup of distant objects. There's MIRI, the mid-infrared instrument, which looks at even longer wavelengths of infrared light, revealing cooler objects and dust structures. And there's the fine guidance sensor, which helps Webb point with incredible precision and also contributes to scientific observations. Together, these instruments turn Webb into more than just a camera. They make it a kind of cosmic laboratory, capable of not only showing what things look like, but also revealing what they're made of, how hot they are, how fast they're moving, and how they change over time. When Webb released its first images to the public, the reaction was immediate and widespread. Nebulae appeared as towering sculpted landscapes of gas and dust. Distant galaxies filled the frame in numbers that seemed almost impossible to count. The level of detail and depth in these images made familiar objects feel new again. But for scientists studying the Milky Way and its centre, Webb offered something particularly valuable. Infrared light, as we've noticed, can slip through dust that blocks visible light. This means Webb can peer into regions of the galaxy that were previously hidden or only partially visible. The crowded, dusty core of the Milky Way, where Sagittarius A resides, is one of those regions. Webb sensitivity allows it to detect faint stars and subtle variations in brightness that older instruments might miss. Its stability, floating in the quiet environment of space rather than sitting under a turbulent atmosphere, means it can make precise, consistent measurements over long periods. This combination is especially important for studying change. The environment around Sagittarius A is not static. Gas moves, stars orbit, magnetic fields shift, light flickers and flares. To understand what's really happening, scientists need to observe not just how things look at one moment, but how they evolve over time. Webb can return to the same region again and again, measuring changes in brightness and structure, with a level of precision that helps reveal patterns in the activity near the black hole. These patterns, in turn, can be compared to theoretical models, helping scientists test their ideas about how matter behaves in such extreme conditions. There's something quietly remarkable about the path that light takes in this process. A photon of infrared light might leave a warm cloud of gas near Sagittarius A, begin its long journey across the galaxy, pass through interstellar space for 26,000 years, and finally arrive at Webb's mirror. It reflects off one of those gold-coated segments, gets focused into an instrument, and is recorded as a tiny electrical signal. That signal is then transmitted back to Earth as radio waves, received by an antenna, decoded by computers, and eventually turned into a pixel in an image or a data point in a graph. That chain of events connects a distant hidden region of the galaxy to a screen, a laboratory, or a quiet room where someone is looking at the results. It's a connection built on layers of engineering, physics, and patience. Webb's role in studying Sagittarius A is not about capturing a single, dramatic picture of the black hole itself. The black hole remains invisible, defined by what it doesn't let out rather than what it emits. Instead, Webb focuses on the environment around it, the warm dust, the stars, and the gas that respond to its presence. By watching how these elements behave, scientists can infer what's happening near the event horizon, even without seeing it directly. There's also a broader context to Webb's observations. Sagittarius A is just one example of a supermassive black hole. Nearly every large galaxy appears to have one at its centre. Some of these black holes are quiet, like ours. Others are active, bright, and influential on a galactic scale. By studying Sagittarius A in detail, scientists can better understand the range of behaviours these objects exhibit and how they interact with their host galaxies. Webb's infrared capabilities also allow it to study the central regions of other galaxies, even those that are very distant. This means researchers can compare our galactic centre to others across the universe, looking for similarities and differences that might reveal how galaxies and black holes grow together over cosmic time. From a certain perspective, Webb is like a bridge between scales. It looks at the very large, the structure of the universe and the formation of galaxies. It also looks at the very small, the chemistry of planetary atmospheres and the details of star-forming regions. In the case of Sagittarius A, it sits somewhere in between, focusing on a region that is both local, in a cosmic sense, and extreme in terms of physics. There's a quiet elegance in that balance. Webb does not operate alone. Its observations are often combined with data from other telescopes, both on the ground and in space. Radio observatories map large-scale structures and track jets. X-ray telescopes detect high-energy events. Infrared data from Webb fills in the warm, dusty details in between. Together, these different views create a more complete picture of what's happening at the galactic centre. For the scientists involved, this process is not a single moment of discovery, but an ongoing conversation between observation and theory. A new set of data might confirm an existing model, or it might highlight a discrepancy that leads to new questions and revisions. In that sense, Webb is not delivering final answers, it's providing sharper questions. From where you are, listening to this, the idea of a telescope sitting 1.5 million kilometres away, quietly collecting ancient light, might feel both distant and strangely intimate. It's distant in the sense that it operates in a realm far removed from daily life. It's intimate in the sense that the information it gathers eventually becomes part of our shared understanding of the universe we live in. There's a gentle rhythm to that exchange. Light travels outward, data travels back, minds on Earth interpret what they see, new ideas take shape, and then the telescope looks again. As Webb continues its work, the view of Sagittarius A and its surroundings becomes more detailed, more dynamic, and more nuanced. Subtle changes in brightness, patterns in how gas and dust move, and variations in the behaviour of stars all add to a growing picture of what it means to live near a supermassive black hole. In the quiet cold of space, Webb remains in shadow, its sun shield always facing the warmth it blocks, its mirrors always pointed outward. It doesn't rush, it doesn't react, it simply observes, collecting the soft, warm whispers of the universe in a form we can begin to understand. When the James Webb Space Telescope was first imagined, the conversations around it didn't start with black holes, or even with our own galaxy. They began much farther away, in both distance and time. Scientists were thinking about the early universe, about the first galaxies that formed after the Big Bang, about stars that lit up a cosmos that had once been dark and quiet. They wanted a tool that could look so far back that it would, in a sense, watch the universe grow up. That ambition shaped what Webb was actually built to do. The universe is expanding. That simple statement carries with it a subtle but powerful consequence. As space itself stretches, the light travelling through it stretches too. Waves of light that began their journey as energetic short-wavelength radiation slowly get pulled into longer, softer wavelengths as they cross billions of light years. By the time the light from the first galaxies reaches us, much of it has been shifted out of the visible range and into the infrared. If you want to see the universe as it was near its beginning, you can't rely on ordinary light. You have to tune into the infrared. That's one of Webb's core purposes. Its instruments are designed to detect light that our eyes cannot see, light that carries the faint, stretched-out signatures of ancient stars and galaxies. This allows scientists to study objects that are not just far away in space, but far away in time. When Webb looks at a galaxy that formed 13 billion years ago, it is seeing that galaxy as it was when the universe itself was still very young. But that same sensitivity to infrared light turns out to be useful for something much closer to home. Dust, which blocks visible light so effectively, is much less of an obstacle for infrared. The longer wavelengths can pass through clouds of tiny particles that scatter and absorb shorter wavelengths. This means Webb can look into regions of space that have always been hidden behind thick veils of cosmic material. Star-forming clouds, the dense plane of the Milky Way, and the crowded centre of our galaxy all become more accessible when you switch from visible light to infrared. So, while Webb's mission includes looking outward toward the edge of the observable universe, it also includes looking inward, toward the dusty, complex places within our own galaxy. Another major goal for Webb is to study how stars and planets form. Stars are born in cold, dense clouds of gas and dust. These regions are often completely opaque in visible light. If you point a traditional telescope at a star-forming cloud, you might see a dark patch against a background of stars, a silhouette where something is blocking the light behind it. Inside that dark patch, however, new stars are taking shape, their gravity pulling material inward, heating it up, and eventually igniting nuclear fusion in their cores. Infrared light can escape from these clouds more easily than visible light. This allows Webb to see the warm glow of protostars, the swirling disks of material that surround them, and the early stages of planetary systems coming together. By studying these regions, scientists can learn how common planets might be, what kinds of environments they form in, and how systems like our own solar system came to be. That same ability to see warm dust and gas is exactly what makes Webb so valuable for studying the environment around Sagittarius A. The region near the black hole is filled with material that's too cool to shine brightly in visible light, but too warm to be completely dark. It glows softly in the infrared, carrying information about its temperature, composition, and motion. Webb is tuned to pick up that glow with remarkable sensitivity. Beyond just taking pictures, Webb is designed to analyze light in detail. One of its most powerful tools is spectroscopy, the process of breaking light into its component wavelengths, like passing it through a prism. When you do this, you don't just get a rainbow, you get a pattern of bright and dark lines, each corresponding to specific atoms and molecules. These patterns act like fingerprints, allowing scientists to identify what an object is made of, how hot it is, and how fast it's moving toward or away from us. This is crucial for understanding distant galaxies and nearby star-forming regions, but it also plays an important role in studying the galactic center. When gas near Sagittarius A heats up or moves rapidly, its light changes in subtle ways. Spectroscopy can reveal whether material is falling inward, being pushed outward, or orbiting at high speeds. It can show how energy is being transferred through the environment, and how different elements are distributed in the region. In this way, Webb isn't just showing scientists what things look like, it's helping them understand what's actually happening. Another part of Webb's design focuses on stability and precision. Because it operates in space, far from Earth's atmosphere, Webb can make measurements without the constant blurring and distortion caused by turbulent air. This allows it to track small changes in brightness and position over time for objects that vary subtly, like the flickering light near Sagittarius A. This consistency is incredibly important. Imagine trying to listen to a very quiet sound in a noisy room. Even if you have good hearing, the background noise makes it hard to pick out the details. Now imagine stepping into a quiet, empty space where the only thing you can hear is that soft sound. Suddenly the subtle variations become noticeable. Webb's position in space gives it something like that quiet room. This design choice also supports one of Webb's broader scientific goals, which is to study exoplanets, planets orbiting other stars. When a planet passes in front of its star, it blocks a tiny fraction of the star's light. Some of that light passes through the planet's atmosphere on its way to the telescope. By analysing how the light changes, scientists can identify molecules in the planet's atmosphere, such as water vapour, carbon dioxide and methane. This kind of work requires extraordinary precision. The changes in light are often measured in parts per million. Webb's stability and sensitivity make these measurements possible. While exoplanets might seem far removed from a supermassive black hole, the underlying design principles are the same. You need to detect faint signals, measure subtle changes, and separate meaningful patterns from background noise. Webb was also designed to be flexible in how it observes. It can take wide field images that capture large regions of space, or it can focus in on specific targets for detailed study. It can observe the same object repeatedly over time, building up a record of how it changes. It can switch between different instruments to look at different wavelengths and gather different kinds of data. This versatility is especially useful for studying a place like the galactic center, where no single type of observation tells the whole story. One moment, scientists might want to map the distribution of stars. The next, they might want to measure the temperature of dust clouds. Later, they might focus on detecting brief flares of energy near the black hole. Webb can support all of these approaches, making it a central piece of a larger observational effort. Another key aspect of Webb's design is its ability to observe very faint objects. Because its mirror is so large and its detectors so sensitive, Webb can collect more light than previous infrared telescopes. This means it can detect objects that are either very distant, very small, or very dim. In the context of the galactic center, this allows scientists to see faint stars that were previously lost in the glare of brighter ones, as well as subtle structures in the surrounding gas and dust. This increased sensitivity also makes it possible to study variations in light that happen over short timescales. If a region near Sagittarius A brightens or dims slightly, Webb can pick up on that change and help scientists understand what might have caused it. There's also a deeper layer to Webb's design that has to do with how it handles data. The telescope itself doesn't send back images in the way a camera on a phone does. It sends back streams of numbers, measurements of how much light hit each detector pixel at each moment. These raw data have to be processed, calibrated, and transformed into something that humans can interpret. This process involves correcting for the telescope's own characteristics, removing background noise, and aligning data from different instruments. It's a careful, methodical procedure that turns faint, scattered signals into clear, meaningful results. In a way, this mirrors the broader goal of the mission. Webb is designed to take the quiet, subtle whispers of the universe and turn them into something we can begin to understand. When scientists planned Webb, they also had to think about longevity. The telescope was built to operate for many years, with enough fuel to maintain its position and orientation well into the future. This long operational life means it can support extended studies that unfold over time, not just one-off observations. For the galactic center, this is especially important. Understanding how Sagittarius A and its surroundings behave requires watching the region over months, years, and even decades. Webb can return to the same area again and again, building up a detailed record of changes and patterns. That kind of dataset allows scientists to move beyond static pictures and into something closer to a story, a narrative of how energy and matter move through one of the most extreme environments in our galaxy. There's also a broader philosophical aspect to what Webb was designed to see. By looking at the earliest galaxies, it helps answer questions about how structure emerged in the universe. By studying star formation, it sheds light on how the basic building blocks of solar systems come together. By analysing exoplanet atmospheres, it explores the potential for life beyond Earth, and by peering into the dusty heart of the Milky Way, it helps us understand the role of supermassive black holes in shaping galaxies. All of these threads connect to a larger question about how the universe evolves, from its earliest moments to the complex structured cosmos we see today. From a technical standpoint, Webb is a machine, a collection of mirrors, sensors, and electronics. But in a broader sense, it's a tool built to extend human curiosity into realms we can't reach ourselves. There's something quietly fitting about the way Webb operates. It sits in the shadow of its own sunshield, always facing away from the warmth and light of the sun, always looking outward into the colder, darker parts of space. It doesn't move quickly. It doesn't react dramatically. It follows a steady routine of pointing, observing, recording, and transmitting. In that steady rhythm, it becomes a kind of listener, tuned to a part of the universe that doesn't speak in bright flashes or loud signals, but in soft, persistent glows and subtle shifts. When Webb turns its instruments towards Sagittarius A, it isn't trying to capture the black hole itself. That remains invisible, defined by absence rather than presence. Instead, it's listening to the environment, to the warm dust, the moving gas, and the stars that respond to the black hole's gravity. It's in those responses that the story unfolds. Light that has been shaped by gravity, by motion, and by magnetic fields carries information about the conditions near the galactic center. Webb's design allows it to capture that information in a way that few other instruments can. There's also a sense of scale in this work that can be easy to overlook. The same telescope that studies the faint atmosphere of a planet orbiting a star dozens of light years away is also studying the crowded, energetic region around a black hole tens of thousands of light years away. It looks at tiny chemical signatures and vast galactic structures with the same set of tools. This ability to move between scales, to connect the very small and the very large, is part of what makes Webb such a powerful addition to astronomy. For the scientists who use it, each observation is a step in a longer process. Data from Webb is combined with data from other telescopes, compared to models, and discussed in papers and conferences. Ideas are tested, revised, and sometimes discarded. Over time, a clearer picture emerges. From where you are, listening to this, the details of detectors and spectrographs might feel far removed from the simple act of looking up at the night sky. But there's a quiet link between the two. When you see a star, you're receiving light that has travelled across space and time to reach you. Webb is doing something similar, just with a different kind of light and a much more sensitive set of eyes. It's collecting those same ancient signals, sorting them, and turning them into information that can deepen our understanding of where we are and how we fit into the larger story of the universe. As Webb continues its work, its design choices, its focus on infrared, its precision, and its patience all come together in a steady flow of observations. Each one adds a little more detail to our picture of the cosmos, and when it looks toward the heart of the Milky Way, it brings with it all of those capabilities, all of that careful planning, all of that quiet attention to subtle signals. The stage is set not just to see something new, but to notice things that were always there, waiting in wavelengths we hadn't fully learned to listen to yet. And in those faint, warm traces of light, there are hints of motion, structure, and change that begin to bridge the familiar and the extreme, the nearby and the distant, the calm of a quiet room, and the restless energy near a supermassive black hole. There's a particular kind of quiet that settles in just before something new comes into view. Not the silence of nothing happening, but the stillness of waiting, of attention focused forward, of a sense that the next moment might carry a detail you've never noticed before. That feeling, that gentle pause between looking and seeing, is a good place to begin when talking about the first infrared glimpses into the region around Sagittarius A. For decades, the centre of the Milky Way had been more of a concept than a landscape. Scientists knew it was crowded. They knew it was active. They knew there was a supermassive black hole sitting at its core, but in many ways their understanding was built from indirect clues, from motion traced over years, from radio signals mapped across the sky, from models that filled in the gaps where direct observation was difficult. Infrared astronomy had already begun to soften those gaps. Ground-based telescopes, equipped with adaptive optics, had revealed individual stars near the black hole, tracked their orbits, and even detected faint flares of energy. But these observations were still limited by Earth's atmosphere, by weather, by the thin veil of heat and turbulence that sits between every ground-based telescope and the stars. When the James Webb Space Telescope finally began to observe the galactic centre, it brought a different kind of presence to the task. It wasn't just another telescope with better resolution. It was a new vantage point entirely, one that floated above the atmosphere, in a cold, stable environment where faint infrared light could be collected with patience and precision. The first time Webb turned its instruments toward the region around Sagittarius A, it wasn't looking for a single dramatic moment. There was no expectation of a sudden reveal, no cosmic curtain being pulled back in a flash of light. Instead, the goal was to gather data slowly, carefully, to let the subtle details of the region accumulate into something meaningful. Infrared light, unlike visible light, doesn't announce itself brightly. It arrives as a soft signal, a gentle warmth, rather than a sharp glow. Detecting it is less like seeing a spotlight and more like feeling the warmth of a distant fire on your face. It's there, but you have to pay attention to notice it. As Webb's detectors began to collect this light, scientists started to see the galactic centre not as a dark void with a few scattered points of brightness, but as a layered environment filled with structure. The first images and data sets revealed a dense field of stars, many of them packed so closely together that their light blended into a kind of soft, grainy glow. Some of these stars were familiar, already catalogued by previous observations. Others were fainter, smaller, and had gone unnoticed before, hidden in the glare of brighter neighbours or obscured by dust that Webb's infrared vision could now peer through. What stood out wasn't just the number of stars, but their variety. There were young, hot stars shining brightly in infrared, their energy carving out small pockets of clarity in the surrounding dust. There were older, cooler stars, glowing more softly, contributing to a kind of background warmth in the region. And there were areas where stars were conspicuously absent, replaced by dense clouds of gas and dust that appeared as darker patches, even in infrared light. These clouds weren't just passive obstacles. They were active participants in the environment, shaped by gravity, stirred by stellar winds, and sometimes heated by nearby stars or energetic events closer to the black hole. One of the first things scientists noticed was how much depth the region seemed to have. Instead of a flat, two-dimensional scene, the galactic centre appeared layered, with structures at different distances overlapping in complex ways. Some stars were clearly in the foreground, closer to Earth. Others were deeper in the core, their light travelling through thicker layers of dust before reaching Webb's mirror. This sense of depth made the region feel more like a three-dimensional landscape than a distant point on a map. It suggested that understanding what was happening near Sagittarius A would require not just looking at where things were on the sky, but also figuring out how far away they were and how they moved through space. As Webb continued to observe, it began to pick up subtle variations in brightness that changed over time. These weren't dramatic flares at first glance. They were gentle shifts, small increases and decreases in the infrared glow of certain areas. But when scientists plotted these changes, patterns began to emerge. Some regions brightened and dimmed on timescales of hours. Others showed slower variations over days. These changes hinted at ongoing processes, at energy being released and redistributed in the environment around the black hole. One of the likely sources of this variability is the flow of gas and dust near Sagittarius A. As material moves through the region, it can heat up, cool down, compress, and expand. Each of these processes affects how much infrared light it emits. Another potential contributor is the interaction between charged particles and magnetic fields. When magnetic field lines twist and reconnect, they can release bursts of energy that heat nearby material, causing it to glow more brightly for a short time. Webb's sensitivity made it possible to track these subtle events with a level of detail that hadn't been achievable before. Instead of seeing the galactic center as mostly steady with occasional outbursts, scientists began to see it as a place of constant low-level activity, a kind of background hum of energy that never fully stops. There was also the matter of motion. By comparing images taken at different times, researchers could see tiny shifts in the positions of stars. Over weeks and months, these shifts added up, tracing out the orbits of stars around the central mass. This wasn't entirely new, but Webb's precision allowed for more detailed tracking, especially of fainter stars that had been difficult to follow before. These stellar motions serve as a kind of map of the gravitational field near the black hole. Each orbit is shaped by the combined pull of Sagittarius A and the surrounding stars and gas. By analysing these paths, scientists can refine their estimates of the black hole's mass and better understand how gravity is distributed in the region. One of the quiet revelations from these first infrared glimpses was just how interconnected everything seemed. Stars weren't just isolated points of light. They were part of a dynamic system, influencing and being influenced by the gas and dust around them. The black hole wasn't just a distant anchor. Its presence subtly shaped the flow of material and the motion of stars across a wide area. In some places, Webb's images revealed filaments of dust, thin, thread-like structures that seemed to trace the outlines of magnetic fields or the paths of past energetic events. These filaments glowed faintly in infrared, their shape suggesting that forces other than simple gravity were at work in sculpting the environment. These kinds of details are easy to miss if you're looking for something dramatic. They don't jump out in a single frame. They become noticeable when you spend time with the data, when you compare one observation to another, when you let patterns slowly emerge. There's a parallel here to how we notice things in our own lives. A single moment might feel ordinary, but when you look back over a stretch of time, small changes and subtle trends begin to stand out. The galactic center, seen through Webb's steady gaze, invites that same kind of long view. Another aspect of Webb's first observations was the way they combined different wavelengths of infrared light. Webb doesn't just look in one narrow band of infrared. It can observe across a range of wavelengths, each of which highlights different physical conditions. Shorter wavelength infrared tends to show hotter objects, like young stars or heated gas. Longer wavelength infrared reveals cooler dust and more diffuse structures. By layering these views together, scientists can build a more complete picture of the region. A bright spot in one wavelength might correspond to a warm star. A dark patch in another might indicate a dense dust cloud. Together, these details help piece together the physical layout of the environment around Sagittarius A. This multi-wavelength approach also allows researchers to track how energy moves through the region. If an area suddenly brightens in shorter wavelength infrared, and then, a little later, in longer wavelength infrared, it can suggest that something heated the material and that the heat then spread or dissipated over time. These kinds of observations turn the galactic center into a kind of laboratory for studying extreme physics. The conditions near Sagittarius A are unlike anything we can create on Earth. Gravity is intense, magnetic fields are strong, speeds are high, matter is often in a hot ionized state. By watching how these elements interact, scientists can test theories about how energy and matter behave under such conditions. One of the more subtle but important outcomes of these first infrared glimpses was a shift in how scientists thought about the quiet nature of our black hole. Sagittarius A is still considered relatively calm compared to the blazing centers of some distant galaxies. It doesn't have a bright, continuous accretion disk. It doesn't produce long, powerful jets that stretch across intergalactic space. But Webb's observations suggested that calm doesn't mean inactive. Instead of long, dramatic outbursts, the region appears to be filled with frequent small-scale events. Tiny flares, gentle pulses of brightness, and ongoing motions that keep the environment in a constant state of subtle change. This picture is less like a sleeping giant and more like a quietly busy workshop, where things are always being moved, adjusted and reshaped, just not in a way that's obvious from far away. There's also a sense of scale that comes through in these observations. The structures Webb is seeing, the filaments, the clouds, the star clusters, all exist on distances that are enormous by everyday standards. A filament that spans a fraction of a light year is still trillions of kilometers long. A star cluster might contain thousands of stars within a region that would dwarf our entire solar system. And yet, in the context of the galaxy, these features are part of a relatively small central region, a tiny fraction of the Milky Way's full size. This contrast between the immense and the intimate is part of what makes the galactic centre such a compelling place to study. It's a region where the largest forces in the universe operate on scales that, while still vast, are small enough for us to observe in detail. From a human perspective, there's something quietly grounding about that. We often think of the universe as either overwhelmingly large or impossibly small. The galactic centre sits in a kind of middle ground. It's far enough away to feel remote, but close enough in cosmic terms for us to watch it change and evolve. As Webb's first data sets were analysed and shared among researchers, the initial excitement wasn't about a single headline-grabbing discovery. It was about the richness of the view, the sense that a door had opened onto a place that had been only partially visible before. There was more there than expected. More stars, more structure, more variability. This didn't immediately overturn existing theories, but it did add layers of complexity. Models of the region had to account for this constant low-level activity, for the interplay between stars, gas, dust and magnetic fields that Webb's observations were revealing. In practical terms, this meant refining simulations, adjusting assumptions, and looking for ways to explain the patterns in the data. In a broader sense, it meant rethinking what it means for a supermassive black hole to be quiet. Quiet, it seems, doesn't mean still. It means active on a different scale in a different way. From where you are now, the idea of a place 26,000 light-years away changing from hour to hour might feel abstract. After all, we tend to think of distant cosmic objects as static, as fixed points in a grand, unchanging sky. Webb's observations gently challenge that idea. Even at the heart of the galaxy, things are in motion. Light shifts, matter moves, energy flows. The universe is not a frozen backdrop, it's a process. There's a certain calm that comes from noticing that. Not the calm of nothing happening, but the calm of steady, ongoing change, of patterns unfolding over time without hurry or urgency. As Webb continues to collect data, these first glimpses are becoming part of a growing timeline. Each new observation adds another layer, another frame in a long, slow-moving sequence that shows how the environment around Sagittarius A evolves. This timeline will eventually stretch over years, perhaps decades, offering a view of the galactic centre that's not just a snapshot, but a kind of quiet film, a record of subtle motions and gentle variations. And in that record, scientists are beginning to see hints of deeper processes, of how gravity and magnetism work together, of how material circulates near a black hole, of how stars and gas coexist in one of the most extreme neighbourhoods in the galaxy. These hints don't arrive as clear answers, they arrive as patterns, as questions, as small details that invite closer attention. So, as we linger with these first infrared glimpses, it's worth holding on to the idea that what Webb is really offering isn't a final picture. It's a way of seeing that's still unfolding. The darkness around Sagittarius A isn't being banished by a single beam of light. It's being gently explored, one wavelength at a time, one observation after another, through a process that's as patient as it is precise. And in that slow unveiling, there's room for both scientific curiosity and a quieter kind of wonder, the kind that doesn't rush to conclusions but stays with a view long enough to notice how it changes. If you sit quietly in a dark room for a while, your eyes begin to notice things they missed at first. A faint reflection in a window, the soft glow of a device across the room, the way shadows shift when a cloud passes over a distant streetlight. Nothing dramatic happens, but the longer you watch, the more the small changes start to stand out. There's a similar feeling in the way scientists began to look at the light coming from the region around Sagittarius A, once Webb started sending back steady, patient streams of infrared data. At first, it all seemed like a soft, constant glow, warm dust, clusters of stars, a general background brightness shaped by countless overlapping sources. But as the data accumulated and as researchers began to compare one observation to the next, patterns began to emerge. The light wasn't as steady as it appeared. It flickered, it shifted, it pulsed in ways that were too subtle to notice in a single snapshot but clear when seen over time. These changes didn't announce themselves with dramatic flares or obvious explosions. They were more like a quiet conversation happening just below the surface of the data. A slight brightening here, a gentle dimming there, a region that seemed calm one day and a little more energetic the next. The kind of variations that invite you to lean in closer rather than step back in surprise. One of the first things scientists noticed was how widespread this variability seemed to be. Instead of a single point of activity near the black hole, there were small changes happening across the surrounding region. Some were tied to individual stars, others appeared in patches of gas and dust, and a few seemed to be linked to the area closest to Sagittarius A, where gravity and magnetic fields are strongest. This suggested that the environment wasn't being shaped by one dominant process, but by many overlapping ones, each contributing its own small influence to the overall pattern of light. To understand what might be causing these flickers, it helps to think about what produces infrared light in the first place. Infrared light often comes from warmth. A star emits it because its surface is hot. A cloud of dust emits it because it has absorbed energy from nearby stars or other sources and is slowly radiating that energy back into space. Gas can emit it when it's heated by collisions, shocks, or radiation. So when a region brightens in infrared, it usually means something there has gotten warmer. When it dims, it's cooling down or the source of heat has changed. Near Sagittarius A, there are many ways for things to heat up. Gas clouds can collide and compress, raising their temperature. Stars can pass close to dust clouds, bathing them in radiation. Magnetic fields can twist and snap, releasing bursts of energy that heat nearby material. And of course, material can move closer to the black hole, where gravitational energy gets converted into heat as it falls inward. Each of these processes leaves a signature in the infrared light, but the signatures often overlap, making it a challenge to separate one cause from another. One particularly intriguing aspect of Webb's observations was how often these small changes occurred. Instead of rare, isolated events, the data suggested a near-constant background of activity. It wasn't a steady glow. It was more like a low, ongoing shimmer, with tiny variations rippling through the region on timescales of minutes, hours, and days. This raised an interesting question. Was the galactic centre more active than scientists had realised, or were they simply seeing it more clearly for the first time? In some ways, it was probably a bit of both. Previous telescopes had detected flares near Sagittarius A, but they were usually larger, more obvious events. Smaller, more frequent changes might have been lost in the noise, blurred by the atmosphere, or masked by the limitations of earlier instruments. Webb's sensitivity and stability allowed it to pick up on these quieter signals, revealing a level of fine-grained activity that had been difficult to observe before. One area of particular interest was the region closest to the black hole's influence, where the flow of gas and dust becomes more chaotic. In this inner zone, material doesn't move in smooth circular orbits. It follows tangled, turbulent paths, influenced by gravity pulling inward and by magnetic fields pushing and twisting in different directions. As clumps of gas move through this environment, they can be heated and stretched, sometimes producing brief increases in brightness. These events might last for only a short time, but when you watch continuously, they add up to a picture of constant motion. There's a kind of rhythm to it, not a regular beat, but a pattern of activity that never quite settles into complete stillness. Another source of unexpected light variations comes from the stars themselves. Some of the stars near the galactic centre are young and massive. They burn through their fuel quickly and can be quite energetic. Their radiation can fluctuate as processes on their surfaces change. When these stars pass near clouds of dust, they can heat those clouds unevenly, creating shifting patterns of infrared emission. Other stars are older and cooler, contributing more gently to the background glow. But even these can show small variations, especially if they are part of close binary systems, or if they interact with the surrounding environment. By tracking these changes over time, scientists can learn not just about the black hole, but about the population of stars that live in its neighbourhood. Which ones are young? Which ones are old? Which ones are moving in stable orbits and which ones are on more chaotic paths? Motion, in fact, is one of the most revealing aspects of the light Webb observes. When an object moves toward us or away from us, the light it emits is shifted slightly in wavelength. This is known as the Doppler effect. In everyday life, you might notice it as the change in pitch of a passing siren. In astronomy, it shows up as a shift in the colour or wavelength of light. By analysing these shifts, scientists can measure how fast something is moving and in what direction. Near Sagittarius A, this technique reveals a complex web of motion. Stars swing around the black hole at high speeds, especially when they pass close to it. Gas flows in spirals and streams, sometimes falling inward, sometimes being pushed outward. Even dust grains can be caught up in these movements, tracing out patterns that hint at the underlying forces at work. Webb's spectroscopic instruments allow researchers to detect these motions with remarkable precision. They can measure velocities of tens, hundreds, or even thousands of kilometers per second, all from subtle changes in the infrared light. One of the quieter surprises in these observations was how interconnected the motion seemed to be. Instead of each star or cloud moving independently, there were hints of larger-scale patterns, groups of stars sharing similar orbital planes, streams of gas flowing along preferred paths, filaments of dust aligned in ways that suggested an organizing influence, possibly from magnetic fields. Magnetic fields are invisible, but they leave traces in how charged particles move. Near the galactic center, where the environment is filled with ionized gas, these fields can have a strong influence. They can guide the flow of material, shape the structure of clouds, and even store energy that gets released in sudden bursts. When a magnetic field line becomes twisted and stressed, it can eventually snap and reconnect in a process known as magnetic reconnection. This releases energy, heating nearby material, and sometimes accelerating particles to high speeds. In the infrared data, these events might show up as small, localized brightenings, subtle flickers that appear and fade as the energy dissipates. Seeing these kinds of events in the environment around Sagittarius A helps scientists draw connections between what they observe in our galaxy and what they see in more distant, more active galaxies. The same physical processes, scaled up or down, may be at work in both places. There's also a fascinating interplay between order and chaos in these observations. On one hand, the motion of stars around the black hole follows predictable paths, governed by gravity. Their orbits can be calculated, modelled, and tested against theory. On the other hand, the behaviour of gas, dust, and magnetic fields is far less tidy. It's turbulent, variable, and sensitive to small changes in conditions. The light Webb observes reflects this mix. Some patterns are stable over long periods, others change from one observation to the next. The challenge is to figure out which variations are meaningful signals of underlying processes and which are just the natural noise of a complex system. To do this, Scientists often look for correlations. If a region brightens in one wavelength and then shortly after in another, that might indicate a specific sequence of heating and cooling. If a flare occurs near a certain type of star, it might suggest a connection to that star's activity. If a pattern repeats over time, it might point to a regular process, like an orbit or a cycle in a magnetic field. This kind of analysis turns the data into a kind of story, where each flicker and shift becomes a clue. There's a quiet satisfaction in that process. It's less about dramatic discoveries and more about patient interpretation, about letting the patterns speak for themselves over time. One particularly interesting area of study involves the inner edge of the material swirling around the black hole. This is the region where the gravitational pull becomes strong enough that material starts to spiral inward more rapidly. It's also where magnetic fields and turbulence can have especially dramatic effects. Webb's observations suggest that this region is far from smooth. Instead of a simple, uniform flow, it appears to be clumpy and variable. Small pockets of material may heat up and brighten as they move inward, then cool or disperse as they interact with other parts of the flow. These events are often subtle, but when you watch them over time, they create a sense of constant, gentle motion, like leaves drifting along a slow-moving stream. There's something almost calming about that image, not because the forces involved are gentle, but because the pattern is steady. Change is the norm, not the exception. Another layer of complexity comes from the fact that we're seeing all of this with a time delay. The light Webb collects left the galactic center about 26,000 years ago. Every flicker, every motion, every subtle change we observe is a record of something that happened long before any human looked up at the sky and wondered what lay at the heart of the Milky Way. This doesn't diminish the value of the observations, but it adds a kind of temporal depth to them. We're not just watching a place far away, we're watching a place far away in time. In a sense, Webb's data is a kind of archive, a record of the galactic center's behavior during a particular era in its long history. As years go by and more observations are added, that archive will grow, allowing scientists to compare different periods and look for longer-term trends. This opens up the possibility of studying cycles of activity. Are there periods when Sagittarius A and its surroundings are more energetic? Are there quieter phases? How long do these phases last? Answering these questions requires patience, not just on the scale of hours or days, but on the scale of years and decades. For now, the focus is on understanding the immediate patterns, the strange light, the unexpected motion, the subtle flickers that Webb has begun to reveal. These details may not make for dramatic headlines, but they are the building blocks of a deeper understanding. Each small variation tells us something about the physical conditions in a region where gravity, magnetism, and motion come together in extreme ways. Each pattern helps refine models and test ideas about how black holes interact with their environments. There's also a broader implication to this work. By understanding the quiet, low-level activity around a relatively calm black hole like Sagittarius A, scientists can better interpret what they see in more distant, more active systems. The same processes, operating at higher intensities, may be responsible for the dramatic phenomena observed in quasars and active galactic nuclei. In that sense, the galactic center becomes a kind of reference point, a place where the fundamental physics can be studied in a more manageable, less overwhelming form. From a human perspective, there's something quietly grounding about focusing on these small details in such a vast context. The universe is often presented as a place of enormous dramatic events, exploding stars, colliding galaxies, black holes tearing matter apart. Those things certainly happen, but there's also a slower, softer side to cosmic activity, a steady background of motion and change that doesn't make headlines, but shapes the long-term evolution of galaxies. Webb's observations bring that side into view. They show a galactic center that is not frozen in time, not a static backdrop, but a living environment full of small movements and gentle shifts. If you let your thoughts settle into that idea for a moment, it can feel surprisingly familiar. Our own lives are often shaped more by small, consistent changes than by rare, dramatic moments. A routine that slowly evolves, a habit that subtly shifts, a pattern that only becomes clear when you look back over a long stretch of time. In the same way, the story of Sagittarius A and its surroundings is being written not just in big, obvious events, but in the quiet accumulation of flickers and motions that Webb is now beginning to track. As scientists continue to analyse these patterns, they're starting to piece together a more nuanced picture of how energy and matter move through the heart of the Milky Way. It's a picture that's less about a single, dominant force and more about a network of interactions, each one contributing to the overall behaviour of the region. This kind of understanding doesn't arrive all at once. It builds slowly, observation by observation, insight by insight, and in that slow build there's room for both careful analysis and a quieter kind of appreciation, for noticing the way even the most extreme places in the universe can be shaped by small, persistent changes. So, as we linger with these strange lights and subtle motions, it's worth remembering that what we're really seeing is not just the behaviour of a black hole's environment, but a glimpse into the ongoing process of a galaxy being shaped from the inside out. The flickers in the infrared are like the pulse of a distant heart, not loud enough to hear without special instruments, but steady enough to remind us that even at the centre of everything, nothing is truly still. When you picture a black hole, it's easy to imagine a simple scene. A dark circle in the middle, a neat ring of light around it, and then empty space beyond. That image, while useful as a starting point, smooths over a lot of what's really happening in the region just outside the event horizon. The space around Sagittarius A is not tidy, it isn't calm, it isn't arranged in clean, perfect layers. It's a place where order and disorder overlap, where structures form and break apart, where dust drifts, disks twist, and gravity constantly rearranges the scene. To understand this environment, it helps to begin with the idea of an accretion flow. Matter doesn't usually fall straight into a black hole. Instead, it tends to approach from many directions, carrying its own motion and momentum. As this material gets closer, it begins to spiral, forming a flattened, rotating structure. In very active black holes, this structure becomes a bright, well-defined accretion disk, glowing intensely as friction and gravity heat the material to extreme temperatures. Sagittarius A doesn't have a classic bright disk like that. Its feeding rate is relatively low, and the material around it is more spread out, more turbulent. Instead of a smooth, shining disk, astronomers often describe the region as having a hot, diffuse accretion flow. It's still rotating, it's still spiralling inward, but it's puffed up, clumpy, and irregular. This is where the disks, dust, and chaos really come into play. Farther out from the event horizon, there are large structures of gas and dust that orbit the central region. One of the most notable is the circumnuclear disk, a ring-like formation of dense material that sits several light-years from the black hole. This structure acts like a kind of reservoir, holding vast amounts of gas and dust that can, over long periods, drift inward or form new stars. The circumnuclear disk isn't a smooth, uniform ring. It's made up of clumps and filaments, denser pockets of material connected by thinner streams. Gravity pulls on these clumps, causing them to move, collide, and sometimes collapse. When they collapse, new stars can form, adding fresh sources of light and energy to the already crowded environment. Closer in, the structure becomes more complex. As material moves inward from the larger disk and surrounding clouds, it enters a region where the black hole's gravity becomes the dominant force. Here the motion of gas and dust speeds up, temperatures rise, magnetic fields grow stronger and more tangled. In this zone, the accretion flow is not a simple flat disk. It's more like a thick roiling cloud of hot plasma, threaded with magnetic field lines and constantly reshaped by turbulence. Some parts of this flow drift inward, losing energy and angular momentum. Other parts get pushed outward by pressure and magnetic forces, creating winds that carry material away from the black hole. This push and pull creates a dynamic balance. Sagittarius A is not just swallowing everything that comes near, it's also, in a sense, breathing, with material moving in and out, circulating through the region. Dust plays an interesting role in this process. Dust grains are tiny, but they carry significant influence. They can absorb and emit radiation, helping to cool or heat the surrounding gas. They can provide surfaces for chemical reactions, allowing molecules to form and change, and they can trace the structure of the environment, outlining filaments and flows in a way that gas alone might not. In the harsh conditions near the black hole, dust doesn't always survive. High temperatures and intense radiation can destroy grains, breaking them down into simpler components. But in slightly cooler, more sheltered regions, dust can persist, drifting along with the gas and marking the paths of larger-scale motions. Webb's infrared vision is particularly well suited to picking up the glow of this dust. When dust grains absorb energy, they warm up and emit infrared light. This allows scientists to map out where the dust is, how warm it is, and how it's distributed around the galactic center. One of the things these observations have revealed is that the dust structures near Sagittarius A are anything but symmetrical. Instead of neat circular rings, there are arcs, streamers, and filaments that curve and twist in different directions. Some of these features appear to be shaped by the gravitational pull of the black hole and nearby stars. Others seem to follow the lines of magnetic fields, which can guide the motion of charged particles and influence the flow of gas and dust. Magnetic fields are an invisible but powerful presence in this region. Near the black hole, gas is often ionized, meaning its atoms have lost or gained electrons and carry an electric charge. Charged particles respond strongly to magnetic fields, spiraling around field lines and moving along them. This can create large-scale structures, like long, thin filaments of material aligned in specific directions. These filaments can stretch across significant distances, connecting different parts of the environment and channeling energy and matter through the region. In some cases, they may act as pathways for material to move inward or outward, linking the larger circumnuclear disk to the inner accretion flow. Where magnetic fields become twisted and stressed, they can store energy. When they reconnect, releasing that energy, nearby material can be heated and accelerated. This process is one of the leading explanations for some of the subtle flares and flickers of light observed near Sagittarius A. The interplay between gravity and magnetism is one of the defining features of this environment. Gravity pulls everything inward, toward the event horizon. Magnetic fields can push back, guiding and sometimes resisting that inward flow. The result is a complex, ever-changing pattern of motion, where material doesn't simply fall in a straight line, but follows curved, looping paths shaped by both forces. Closer still to the black hole, the flow of material becomes even more extreme. In this inner region, speeds can approach a significant fraction of the speed of light. Temperatures can rise to millions of degrees. The distinction between gas and plasma becomes more pronounced, as atoms are stripped of their electrons and matter takes on a more energetic, charged state. This is also where the effects of Einstein's theory of relativity become especially important. Space and time are warped by the black hole's mass. Paths that would be straight in normal space become curved. Light itself bends, following the shape of the distorted space-time around the event horizon. This warping influences how we see the region. The light Webb and other telescopes collect has already been bent, stretched, and shifted by the time it reaches us. What appears as a ring or arc in an image might be light from material on the far side of the black hole, curved around into our line of sight. The famous shadow of the black hole, captured by the Event Horizon Telescope, is an example of this effect. It's not a simple silhouette. It's a region where light that would otherwise reach us is pulled into the black hole, leaving behind a dark area surrounded by a bright ring formed by light that has been bent around the event horizon. Around that shadow, the environment is anything but simple. Material in the accretion flow moves in complicated three-dimensional patterns. Some of it may be on stable orbits for a time. Some of it spirals inward, crossing the point of no return. Some of it gets flung outward, carried away by winds or jets. Jets, in fact, are another feature often associated with black holes, though Sagittarius A does not currently produce the kind of long, powerful jets seen in some active galaxies. There is evidence, however, of outflows and past activity that suggest it may have been more energetic in the past. The large, bubble-like structures extending above and below the plane of the Milky Way hint at periods when the black hole released significant amounts of energy, possibly driving material outward over thousands of light years. These features serve as a reminder that the calm phase we see now is just one chapter in a much longer story. The region near the event horizon is also influenced by the stars that pass close by. Some stars follow highly elongated orbits that bring them near the central black hole, before carrying them back out into the wider galactic core. When a star passes close, its gravity can disturb the surrounding gas and dust, stirring up the accretion flow and potentially triggering small bursts of activity. In rare cases, if a star were to pass too close, it could be torn apart by the black hole's tidal forces, creating a dramatic flare as its material is stretched and heated. While no such event has been directly observed near Sagittarius A in recent times, the possibility adds another layer of complexity to the environment. All of this contributes to the sense of controlled chaos in the region. There are structures, like disks and filaments, that persist over long periods. There are also transient features, like clumps of gas or brief flares of light, that appear and fade. The overall pattern is one of constant motion, shaped by forces that operate on both small and large scales. Webb's observations add depth to this picture by revealing how dust and warm gas are distributed in this environment. In some areas, the infrared data shows dense concentrations of dust that appear to shield pockets of gas from the most intense radiation and heat. These sheltered regions can become sites of star formation, even relatively close to the black hole, where conditions might seem too extreme for new stars to form. The presence of young stars near Sagittarius A is one of the intriguing puzzles of the galactic center. Star formation typically requires cold, dense clouds of gas that can collapse under their own gravity. The region near a supermassive black hole is anything but gentle. Gravity, radiation and turbulence all work against the quiet conditions usually associated with stellar birth, and yet there they are, young, massive stars shining brightly in the core of the galaxy. This suggests that the interplay between disks, dust and chaos doesn't just lead to destruction. It can also create pockets of stability, places where material can settle and collapse despite the surrounding turmoil. These pockets are often found in the larger circumnuclear disk and in dense filaments that connect it to the inner region. By studying these structures in infrared, scientists can learn how star formation proceeds in such an extreme environment and how it differs from the process in calmer parts of the galaxy. There's also a connection here to the long-term evolution of the Milky Way. The flow of material toward and away from Sagittarius A plays a role in regulating the central region of the galaxy. If too much material falls in, the black hole could become more active, releasing energy that heats and disperses surrounding gas, slowing down star formation. If too little material is available, the region could cool and allow more stars to form. This feedback loop between black hole activity and the surrounding environment is thought to be a key factor in shaping galaxies over cosmic time. By studying the disks and dust around our own black hole, scientists can gain insight into how this process works in a relatively quiet system. That, in turn, can help them understand more active galaxies, where the same principles may operate on a much larger, more dramatic scale. From a broader perspective, the region around the event horizon is a place where many of the universe's fundamental forces come together. Gravity dominates, pulling everything inward. Electromagnetism shapes the motion of charged particles and magnetic fields. Nuclear processes inside stars add energy and heavy elements to the mix. relativity governs how space and time behave near the black hole. All of these influences overlap in a relatively small volume of space, creating a natural laboratory for extreme physics. Webb's ability to observe the warm dust and gas in this environment provides a new set of tools for exploring that laboratory. By mapping the distribution of material and tracking how it changes, scientists can test their theories about how accretion flows work, how magnetic fields behave, and how energy is transported in such extreme conditions. There's a quiet beauty in the way these complex processes manifest as subtle patterns of light. A filament glowing faintly in infrared might represent a stream of material guided by a magnetic field. A slightly brighter patch might mark a region where gas has been heated by a recent event. A cluster of stars might trace the remnants of a dense cloud that collapsed long ago. Each of these features is a snapshot of an ongoing process, a moment in the long, slow dance of matter around a black hole. From where you are now, the idea of dust drifting and disks twisting around an invisible centre might feel distant, abstract. But there's a kind of connection worth noticing. The same forces that shape this extreme environment also shape more familiar places. Gravity pulls rain toward the ground. Magnetic fields guide the behaviour of charged particles in everyday electronics. Heat flows from warm objects to cooler ones. Motion creates patterns, whether in a stream of water, a swirl of wind, or a spiral of stars. The scale is different, but the underlying principles are the same. As Webb continues to watch the region around Sagittarius A, the picture of disks, dust, and chaos becomes more detailed and more nuanced. Structures that once seemed smooth reveal their clumpy filamentary nature. Regions that seemed quiet show signs of ongoing activity. Patterns that were once hidden in noise become visible in the steady accumulation of data. This process doesn't lead to a single, final image. It leads to a richer understanding of how the environment works as a whole, as a system of interacting parts rather than a simple static scene. In that sense, the chaos around the event horizon isn't something to be smoothed away. It's something to be appreciated, studied, and understood as part of the natural behaviour of matter and energy under extreme conditions. What do these patterns of motion and light tell us about the fundamental nature of black holes? How do they challenge or refine our existing theories? There's a moment in any careful investigation when the data stops behaving exactly the way you expect. Not in a dramatic, everything is wrong sense, but in a quieter, more unsettling way. The numbers still line up, the patterns still make sense, but there's a small mismatch, a subtle detail that doesn't quite fit into the picture you've been carrying in your head. That's often the point where curiosity deepens rather than fades, where scientists lean in instead of stepping back. For many researchers studying Sagittarius A, that moment arrived not with a single dramatic image, but with the steady accumulation of Webb's infrared observations. The general idea of a calm, low-activity black hole surrounded by a relatively thin, inefficient accretion flow had held up well for years. Models predicted occasional flares, slow-moving gas, and a fairly stable environment overall. What Webb began to reveal, however, was a level of activity that felt more constant, more intricate and more widespread than many had anticipated. One of the first surprises was the frequency of change. Instead of long stretches of relative stillness punctuated by rare bursts of energy, the region around Sagittarius A appeared to be in a near continuous state of subtle motion and variation. Light curves, which track how brightness changes over time, showed small rises and dips happening regularly, sometimes on timescales of minutes. These weren't the dramatic flares that earlier instruments had picked up. They were quieter, more modest shifts, but they were persistent. The galactic centre, it seemed, was never truly resting. There was always something happening, always a small exchange of energy, always a gentle rearrangement of material. This raised a fundamental question. If Sagittarius A is considered quiet compared to more active black holes, what does quiet really mean? Does it mean low energy overall? Or does it mean a different style of activity, one that's spread out over time rather than concentrated into bright, obvious events? Webb's data suggested the latter. The environment looked less like a dormant system and more like a place with a steady background of low-level processes, each one too small to stand out on its own, but together creating a complex dynamic whole. Another point of surprise came from how widespread these variations were. Scientists initially expected most of the interesting activity to be concentrated very close to the black hole, near the region where gravity is strongest, and where material is most likely to heat up and emit radiation. But the infrared observations showed changes happening across a broader area, including in regions farther out in the surrounding gas and dust. This implied that whatever was driving the variability wasn't confined to a tiny zone near the event horizon. Instead, it seemed to involve larger-scale structures and processes that extended well into the galactic core. One possibility is that waves of energy or motion were propagating through the environment, linking the inner and outer regions. Another is that the flow of material inward and outward was more interconnected than previously thought, with changes in one part of the system influencing conditions elsewhere. Either way, the picture of a neatly layered structure with a calm outer region and a busy inner zone began to feel too simple. There was also the matter of how quickly some of these changes occurred. Near a supermassive black hole, distances are vast, but so are the forces at work. Even so, some of the observed variations happened on timescales that suggested processes operating in relatively compact regions. For a brightness change to occur over minutes or hours, the source of that change has to be limited in size. Energy can only move so fast. This pointed to activity happening very close to the black hole, in regions where gravity and magnetic fields are intense and where material is moving at high speeds. At the same time, the fact that similar patterns appeared in areas farther out suggested a kind of coupling between different parts of the system. It wasn't just a single hotspot flickering on and off. It was a network of interactions with influences spreading across the environment. Another subtle but important surprise involved the role of magnetic fields. Magnetic fields had long been thought to play a part in shaping the accretion flow, but Webb's observations gave new weight to that idea. The alignment of filaments, the patterns of motion, and the locations of some of the brightness variations all hinted at magnetic structures guiding the behavior of gas and dust. This suggested that magnetism might be just as important as gravity in determining how material moves near Sagittarius A. In some models, magnetic fields can act like invisible scaffolding, shaping the flow of plasma and channeling energy through the system. They can also store energy and release it in bursts through magnetic reconnection, heating material and producing brief flashes of light. The prevalence of small frequent brightenings in the infrared data fit well with this kind of process. Instead of rare, large-scale events, the environment might be experiencing many small releases of magnetic energy, creating a constant background of activity. This idea shifted the focus of some research away from purely gravitational models and toward more detailed magneto-hydrodynamic ones, which take both fluid motion and magnetic fields into account. Another aspect that caught scientists' attention was the apparent lack of a simple, stable accretion structure. While there is evidence of a general inward flow of material, the data suggested that this flow is highly turbulent and inefficient. Much of the gas and dust that drifts toward the black hole doesn't actually make it across the event horizon. Instead, it gets heated, stirred, and often pushed back out into the surrounding region. This inflow-outflow balance had been predicted by some models, but seeing evidence of it in such detail was still striking. It meant that Sagittarius A was not just a passive sink, quietly swallowing whatever came its way. It was part of a dynamic circulation, with material constantly cycling through the region, gaining and losing energy, moving inward and outward in a complex pattern. This has implications for how the galactic center evolves over time. If material is frequently pushed back out, it can mix with the surrounding gas and dust, influencing star formation and the overall structure of the core. The black hole, in this view, is not just an endpoint for matter, but an active participant in shaping its environment, even in its relatively calm state. Another point of interest was how well some aspects of the observations matched existing theories, while others didn't quite line up. The overall mass of the black hole, the general structure of stellar orbits, and the broad distribution of material all fit within expected ranges, but the fine details, the timing and location of the flickers, the apparent connections between different regions, were harder to reconcile with simpler models. This is often where science becomes most interesting. When a model works in broad terms but struggles with the details, it suggests that the underlying principles are on the right track, but that some important pieces are missing or oversimplified. In this case, those missing pieces might involve the exact geometry of magnetic fields, the role of turbulence in the accretion flow, or the way energy is transferred between different parts of the system. Another subtle surprise came from the comparison between Sagittarius A and more active black holes. For a long time, scientists had thought of our black hole as a kind of scaled-down, low-power version of the bright, energetic centres of distant galaxies. The idea was that the same basic processes were at work, just operating at a much lower intensity. Webb's observations suggested that this might not be the whole story. While there are certainly similarities, the pattern of frequent low-level activity seen around Sagittarius A doesn't always have a clear counterpart in more active systems, where large dramatic events tend to dominate the observations. This raised the possibility that black holes might operate in different modes, not just different levels of brightness. In one mode, a black hole might be dominated by a steady, turbulent flow with frequent small energy releases, like what seems to be happening in our galactic centre. In another mode, it might be dominated by a dense, bright accretion disk and powerful jets, producing dramatic, large-scale phenomena. Understanding how and why a black hole transitions between these modes is an open question, and Webb's data adds a new layer of detail to that puzzle. There was also an element of surprise in how the environment seemed to maintain its structure, despite the constant activity. Even with all the flickers, flares, and turbulent motion, the overall layout of stars, dust, and gas remained relatively stable over the periods observed. Filaments stayed in roughly the same places, stellar orbits continued along their predictable paths, the circumnuclear disk retained its general shape. This suggested a kind of balance at work. The system is dynamic, but it's also self-regulating. Energy is constantly being injected and dissipated, but not in a way that dramatically reshapes the region on short timescales. This balance between change and stability is a theme that runs through many areas of astrophysics, but seeing it play out in such an extreme environment was still striking. Another point that drew attention was the way the observations highlighted the limits of existing data. Webb's infrared view revealed patterns and variations that had simply been invisible before. This raised the question of how many other features in the universe might be waiting to be noticed, not because they're hidden by distance or dust, but because we haven't been looking in the right way. In that sense, the surprise wasn't just about Sagittarius A, it was about the process of observation itself. By switching to a new wavelength, a new vantage point, and a new level of sensitivity, scientists didn't just refine an existing picture. They uncovered a layer of complexity that had been largely unrecognized. This is a reminder that our understanding of the universe is always shaped by the tools we use to observe it. When those tools change, the universe in a way changes too, not in reality, but in how it appears to us. There was also a human side to the surprise. Many of the researchers involved had spent years, sometimes decades, working with models of the galactic centre. They had built careers around certain assumptions and interpretations. Seeing data that challenged or complicated those views wasn't just a technical matter, it was a personal one. This doesn't mean the old models were wrong, it means they were incomplete. Science often advances this way, not by discarding what came before, but by layering new details on top of it, making the picture richer and more nuanced. In practical terms, this has led to a flurry of new simulations and theoretical work. Researchers are adjusting their models to include more detailed magnetic field structures, more realistic turbulence, and more complex interactions between different components of the system. They're running these models forward in time and comparing the results to Webb's observations, looking for matches and mismatches. This back and forth between data and theory is where much of the real work happens, quietly and methodically, far from the headlines. Another surprising element was how well the observations fit into a broader context of galaxy evolution. The idea that black holes and their host galaxies influence each other over long timescales is well established. Active black holes can regulate star formation by heating and dispersing gas. Galaxies can feed their black holes by funneling material inward. What Webb's data suggested is that even in a relatively calm system like the Milky Way, this interaction is ongoing, just at a lower intensity. The constant low-level activity near Sagittarius A might be part of a long-term feedback process, gently shaping the central region of the galaxy over millions of years. This adds a layer of significance to the flickers and motions observed. They're not just local curiosities. They may be part of a much larger, slower story about how galaxies and black holes grow and change together. There's also something quietly striking about the scale of the surprise. No single observation overturned decades of research. There was no dramatic announcement that everything we thought we knew was wrong. Instead, there was a gradual realization that the system was more complex, more active, and more interconnected than previously appreciated. It's the kind of surprise that unfolds slowly, like noticing that a familiar place has more depth and detail than you remembered when you take the time to really look at it. From where you are now, the idea of scientists being shocked by subtle variations in infrared light might sound a bit understated. But in a field where expectations are built on years of careful measurement and modelling, even a small, persistent discrepancy can be a big deal. It points to something new to understand, something that might lead to deeper insights about the nature of black holes, galaxies, and the forces that shape them. There's also a philosophical layer to this. The fact that a supermassive black hole, an object often portrayed as simple and final, turns out to be surrounded by such a rich, dynamic environment, is a reminder that even the most extreme things in the universe are part of larger systems. Nothing exists in isolation. Everything interacts, influences, and responds. In that sense, the surprise isn't just about light flickering or gas moving. It's about the realization that the heart of the Milky Way is not a static, finished thing. It's a process, unfolding over time, shaped by countless small interactions as much as by its central massive presence. As Webb continues to observe, more of these subtle surprises are likely to emerge. Patterns that seem clear now might become more complicated. New connections might be noticed. The picture might shift again, not in a dramatic, headline-grabbing way, but in the slow, steady way that deeper understanding often does. For now, what stands out most is the sense of liveliness in a place that was once thought of as relatively quiet. The strange light, the unexpected motion, the subtle flickers, and the constant low-level activity all point to a region that is, in its own understated way, busy. And in that busyness, there's a quiet invitation. An invitation to keep watching, to keep refining our models, to keep paying attention to the small details that might hold the keys to larger truths. How do these observations change our understanding of black holes in general? What do they suggest about the role Sagittarius A plays in the life of the Milky Way? There's a certain elegance to the way invisible things leave visible traces. You can't see the wind, but you can watch leaves move. You can't see gravity, but you can follow the path of a falling object. And in the crowded, energetic region around Sagittarius A, you can't see the magnetic fields themselves, but you can begin to sense their presence through the way light flickers, gas flows, and dust lines up in long, delicate patterns. When scientists started to look closely at the time variations in Webb's infrared data, they weren't just seeing changes in brightness, they were seeing hints of an underlying structure, something guiding and shaping those changes, something that couldn't be explained by gravity alone. Magnetic fields quickly moved to the center of that conversation. To understand why, it helps to take a small step back and think about what magnetic fields do in space. On Earth, magnetism often feels like a quiet, familiar force. A compass needle points north, a magnet sticks to a refrigerator, electric motors spin. In space, magnetism operates on a much larger, more dramatic scale. When gas becomes hot enough, its atoms lose or gain electrons, turning into charged particles. This state of matter is called plasma, and plasma responds strongly to magnetic fields. Near Sagittarius A, much of the gas is in this charged plasma state. That means it doesn't just drift under the influence of gravity, it also follows the invisible pathways of magnetic field lines, spiraling around them, sliding along them, and sometimes getting trapped by them. These field lines can stretch, twist, and tangle as the gas moves. When they become too stressed, they can suddenly snap and reconnect in a new configuration. This process, known as magnetic reconnection, releases energy, sometimes in the form of heat, sometimes in the form of fast-moving particles. In many parts of the universe, from the surface of the Sun to the environment around distant galaxies, magnetic reconnection is a key driver of energetic events. Near Sagittarius A, it appears to play a similar role, but in a setting where gravity and motion are already operating at extreme levels. Webb's observations don't show magnetic fields directly, but they show the consequences of their actions. One of the clearest signs is the pattern of time variations in the infrared light. Some regions brighten and dim in ways that are difficult to explain purely by the slow movement of gas or the steady glow of stars. The changes can be too fast, too localized, or too frequent. These characteristics point towards sudden releases of energy, rather than gradual heating or cooling. Imagine a stretched rubber band. As you pull it, you store energy in its tension. When it snaps back, that energy is released quickly. Magnetic fields can behave in a similar way. As gas moves and drags the field lines with it, the lines can become twisted and stressed. When they reconnect, the stored energy is released into the surrounding plasma, heating it and causing it to glow more brightly for a short time. In the infrared data, this might appear as a small flare, a patch of light that briefly intensifies before fading back into the background. What surprised scientists was not just that these events seemed to happen, but how often. Instead of rare, dramatic bursts, the region around Sagittarius A appeared to be dotted with frequent low-level energy releases. It was as if the environment was constantly adjusting, releasing small amounts of tension over and over again rather than building up to a single large event. This kind of behavior fits well with a turbulent magnetized plasma, where countless small-scale interactions are happening all the time. The idea of turbulence is important here. In everyday life, you might see turbulence in the way smoke curls and twists as it rises from a candle, or in the way water swirls around rocks in a stream. It's a state where motion becomes chaotic, where small disturbances grow and interact, creating complex, ever-changing patterns. Near a black hole, turbulence can be driven by many factors. Gravity pulls material inward. Rotation causes it to shear and stretch. Magnetic fields add another layer of force, guiding and resisting motion in different directions. The result is a highly dynamic environment where energy is constantly being transferred between different forms and scales. Webb's time series observations, which track how brightness changes over minutes, hours, and days, give scientists a window into this turbulent behavior. Instead of a smooth curve, the light output from certain regions looks more like a gently jagged line, full of small peaks and dips. Each one represents a tiny shift in conditions, a small release of energy, a momentary change in how matter and fields are interacting. There's a quiet complexity in that pattern. It suggests that the environment near Sagittarius A is not dominated by a single simple process, but by a web of interactions, each one influencing the others. Another clue to the role of magnetic fields comes from the shapes of the structures seen in infrared images. Filaments of dust and gas often appear aligned in specific directions, forming long, thread-like features that cut across the region. These alignments are difficult to explain if gravity alone is shaping the material. Gravity tends to pull things inward, creating more radial or circular patterns. Magnetic fields, on the other hand, can guide charged particles along their lines, creating elongated directional structures. By comparing the orientation of these filaments with models of how magnetic fields might be arranged around the black hole, scientists can begin to infer the likely geometry of those invisible fields. Some evidence suggests that the fields form large-scale patterns that connect the inner accretion flow to the outer circumnuclear disk. This could allow energy and material to move along these magnetic pathways, linking different parts of the environment in a kind of hidden network. Time variations add another layer to this picture. If a magnetic reconnection event occurs in one part of the system, the resulting burst of energy can propagate outward, affecting nearby regions. This might show up as a sequence of brightenings one after another in different parts of the infrared data. Tracking these sequences allows scientists to estimate how fast energy is moving through the system and how different regions are connected. This is where the concept of scale becomes especially interesting. The events Webb is observing are happening in regions that, while enormous by human standards, are relatively compact in astronomical terms. A change that unfolds over a few hours might be happening in a region only a few times larger than the orbit of Mercury, and yet, these small-scale events are part of a much larger system, one that spans light years and influences the structure of the entire galactic core. This connection between the small and the large is one of the most intriguing aspects of the observations. It suggests that what happens close to the black hole, in a relatively tiny volume of space, can have ripple effects that extend far outward, shaping the behavior of gas and dust on much larger scales. Time variations also offer a way to probe the extreme physics near the event horizon. Because the timescale of a change is related to the size of the region where it occurs, fast variations imply small, compact sources. By measuring how quickly brightness changes, scientists can place limits on how close to the black hole those changes are happening. This is a kind of indirect mapping technique. You can't see the event horizon itself, but you can use the timing of the light variations to infer the size and location of the emitting regions. It's like hearing an echo in a canyon and using the delay to estimate how far away the walls are. In the case of Sagittarius A, some of the fastest variations suggest activity happening very close to the black hole, in the inner accretion flow where gravity and magnetic fields are at their strongest. This region is also where the effects of relativity become especially pronounced. As material moves at high speeds and in a strongly curved spacetime, time itself behaves differently. Clocks closer to the black hole run more slowly compared to those farther away. Light paths bend. Orbits precess. While Webb's observations don't directly measure time dilation or spacetime curvature, the patterns of motion and variation they reveal are influenced by these effects. Understanding them requires models that combine gravity, magnetism, and relativity into a single coherent framework. That's a challenging task, and it's one that's still very much in progress. Another fascinating aspect of the time variations is their potential connection to the larger history of the galactic center. The Milky Way's black hole has likely gone through periods of higher and lower activity over millions of years. The large bubble-like structures seen extending above and below the galactic plane suggest that, in the past, Sagittarius A released significant amounts of energy into its surroundings. The low-level, frequent energy bursts seen today might be part of a quieter phase in that long cycle. By studying the current pattern of activity in detail, scientists can look for clues about how the system might change in the future. Will the black hole remain in this calm, turbulent state, or could it eventually transition into a more active phase? Time variations, when tracked over years and decades, can reveal trends and shifts that hint at such changes. There's also a connection to other black holes. The processes observed near Sagittarius A are likely not unique. Magnetic fields, turbulence, and energy bursts are common features in many astrophysical systems, from young stars to active galactic nuclei. By studying these processes in our own galactic centre, where we can observe them in relatively fine detail, scientists can gain insights that apply to black holes across the universe. In more active systems, the same kinds of magnetic reconnection events and turbulent flows may be responsible for the dramatic flares and jets that make those galaxies shine so brightly. In that sense, Sagittarius A serves as a quieter, more approachable example, a place where the same fundamental physics can be studied without being overwhelmed by extreme brightness and energy. There's something gently reassuring about that. It suggests that even the most dramatic phenomena in the universe are built from the same basic processes that operate in calmer settings. The difference is one of scale and intensity, not of kind. From a broader perspective, the interplay between magnetic fields, energy bursts, and time variations highlights a theme that runs through much of modern astrophysics. The universe is not a collection of isolated objects. It's a network of systems, each one influenced by forces that operate across different scales and connect different regions. Near Sagittarius A, gravity pulls material inward. Magnetic fields guide and resist that motion. Turbulence mixes and redistributes energy. Radiation carries information outward, across space and time, to a telescope waiting in the cold shadow of its sunshield. Each of these elements plays a role in shaping what Webb observes. There's a quiet poetry in that chain of events, even if we describe it in the language of physics rather than metaphor. Energy moves, fields twist, light travels, data accumulates, understanding grows. But this growth is slow. The patterns in the time variations don't reveal themselves in a single observation. They emerge over many, as datasets are compared, aligned, and analysed. Researchers look for repeating features, for correlations, for deviations from expected behaviour. This process can take years, and it often leads to more questions rather than fewer. For example, how exactly are the magnetic fields arranged around Sagittarius A? Are they mostly ordered or mostly tangled? How do they evolve over time? What determines where and when reconnection events occur? Each of these questions opens up a new line of investigation. There's also the challenge of connecting observations to theory. Simulating a magnetized, turbulent relativistic accretion flow is one of the most complex tasks in computational astrophysics. It requires enormous computing power and sophisticated algorithms. Even then, models have to make simplifications. Webb's data provides a way to test these models to see which ones reproduce the observed patterns of light and variation and which ones fall short. This back and forth between observation and simulation is where much of the deeper understanding is built. It's a quiet, iterative process, far removed from the dramatic images that often capture public attention. But it's essential for turning those images and light curves into knowledge about how the universe works. From where you are now, the idea of magnetic fields twisting around a black hole and releasing energy in small, frequent bursts might feel both distant and strangely familiar. After all, many of the systems we interact with every day, from electrical circuits to weather patterns, involve similar principles. Energy builds up, forces interact, tension is released, patterns emerge. The scale is different, but the logic is the same. As Webb continues to observe Sagittarius A, the picture of magnetic fields and time variations will become more detailed. New patterns will likely be noticed. Old assumptions may be refined or replaced. For now, what stands out is the sense of a living, breathing environment at the heart of the Milky Way. Not breathing in a literal sense, of course, but in the way it cycles energy and matter, in the way it constantly adjusts and reshapes itself through countless small interactions. Those interactions leave their mark in the infrared light, in the subtle flickers and gentle pulses that Webb records, and as those pulses continue, carried across space and time, they invite us to keep paying attention, to keep following the thread of curiosity that leads from a quiet room on Earth to a region of space where gravity, magnetism and motion come together in one of the universe's most extreme and fascinating settings. For a long time, black holes occupied a very specific place in our collective imagination, both inside and outside the scientific community. They were the ultimate endpoints, the places where things went in and never came back out. Simple in concept, extreme in behaviour, and in many ways isolated from the rest of the universe except for their overwhelming pull on whatever wandered too close. Even in more technical descriptions, black holes often felt like boundaries rather than participants, defined more by what they swallowed than by what they contributed. The growing body of observations around Sagittarius A, especially those coming from Webb and other modern instruments, has been quietly shifting that picture. Instead of seeing a black hole as a kind of cosmic sink, a final destination for matter and light, scientists are increasingly seeing it as part of a much larger, more interactive system. The black hole is still defined by its event horizon, by that invisible boundary where escape becomes impossible, but the region around that boundary is now understood to be a place of ongoing exchange, influence, and connection. This change in perspective doesn't come from a single discovery. It emerges from patterns, from the accumulation of small details that, taken together, suggest a more active role for black holes in shaping their environments. One of the most significant shifts involves the idea of accretion itself. In older, simpler models, accretion was often pictured as a one-way flow. Matter drifts in, spirals closer, heats up, and eventually crosses the event horizon. Energy is released along the way, but the overall direction is inward. The black hole grows. The surrounding region gradually loses material. What Webb's observations and related studies suggest is a more balanced, more dynamic process. Near Sagittarius A, much of the material that moves inward doesn't actually make it all the way in. Instead, it becomes part of a circulating flow. Gas and dust are heated, stirred, and sometimes pushed back outward by pressure, turbulence, and magnetic forces. This creates a kind of feedback loop, where material is constantly cycling through the region, rather than simply disappearing into the black hole. This idea of circulation changes how scientists think about the relationship between a black hole and its host galaxy. If material is frequently pushed back out, it can influence the surrounding environment, affecting things like star formation, gas distribution, and the overall structure of the galactic core. The black hole, in this view, is not just consuming matter, it's also helping to regulate the conditions around it, even in a relatively quiet system like the Milky Way. Another shift in understanding comes from the role of magnetic fields. For a long time, gravity was seen as the dominant force in the story of black holes, and it is, in many ways. The black hole's immense mass shapes the motion of stars and gas on large scales. It bends space-time itself. But the detailed behaviour of material near the event horizon appears to be strongly influenced by magnetism as well. The patterns of light variations, the alignment of filaments, and the frequency of small energy releases all point toward a highly magnetised environment. This means that to fully understand how black holes interact with their surroundings, scientists have to consider not just gravity and motion, but also the complex behaviour of magnetic fields and charged particles. This adds a layer of richness, but also a layer of complexity. Instead of a relatively straightforward gravitational system, the region near a black hole becomes a magneto-hydrodynamic one, where fluid motion, magnetic fields, and gravity are all intertwined. This makes modelling and prediction more challenging, but it also opens up new avenues for understanding how energy and matter move through extreme environments. There's also a change in how scientists think about scale. For a long time, black holes were often divided into two broad categories. There were the small stellar mass black holes formed from collapsing stars and the massive supermassive black holes at the centres of galaxies. The processes that governed them were thought to be similar, just operating at different scales. That idea still holds in many respects, but the detailed observations of Sagittarius A suggest that there may be different modes of behaviour that aren't simply a matter of size or brightness. A black hole like Sagittarius A, with its frequent low-level activity and turbulent, inefficient accretion flow, may represent a different state than a bright, active galactic nucleus with a dense, luminous disk and powerful jets. The transition between these states is not just a matter of turning up or down the same processes. It may involve changes in how magnetic fields are structured, how material is distributed, and how energy is transported. This raises new questions about the life cycles of black holes. Do they all go through similar phases, moving from quiet, turbulent states to bright, active ones and back again? What triggers these transitions? Is it the availability of material, the structure of the surrounding galaxy, or some internal property of the black hole itself? Webb's observations don't answer these questions directly, but they provide a detailed snapshot of one phase, offering a reference point for comparison with more active systems. Another important shift in understanding involves time. Black holes are often described as timeless objects, defined by a few basic properties like mass, spin, and charge. These properties change slowly over long periods as the black hole gains or loses material. The black hole itself, in this sense, can feel almost static. The environment around it, however, is anything but. The frequent time variations observed near Sagittarius A highlight how dynamic the surrounding region is. Energy is constantly being released and redistributed. Material moves, heats, cools, and changes state. Magnetic fields twist and reconnect. This means that when scientists talk about the behaviour of a black hole, they're often really talking about the behaviour of the surrounding environment, not the black hole itself. This distinction is important. The event horizon remains an absolute boundary, but everything just outside it is part of a living system, one that responds to changes on timescales ranging from minutes to millions of years. Understanding black holes, in this sense, becomes less about studying an isolated object and more about studying an ecosystem. There's also a shift in how scientists think about the visibility of black holes. For a long time, the defining feature of a black hole was that it couldn't be seen directly. It was detected through its effects, through the motion of stars or the emission of radiation from infalling material. That's still true. The black hole itself remains invisible, but the environment around it is now being observed in such detail that it almost feels like a stand-in, a proxy for the black hole's presence. The flickers of light, the patterns of motion, and the structures of dust and gas all carry information about what's happening near the event horizon. In a sense, scientists are learning to read these signs, to interpret the behaviour of the invisible object through the visible responses of its surroundings. This is a more subtle, more nuanced form of observation than simply detecting a bright disk or a powerful jet. It requires careful attention to small details and long-term patterns. Another area of change involves the relationship between black holes and star formation. In more active galaxies, there's strong evidence that black hole activity can suppress or enhance star formation by heating or dispersing gas. This is often described as feedback, a process where the black hole influences the evolution of its host galaxy. In the Milky Way, where the black hole is relatively quiet, the role of feedback is less obvious, but the detailed view of disks, dust, and circulating material suggests that even low-level activity can shape the central environment. By pushing material back out, stirring up gas, and influencing the distribution of dust, Sagittarius A may be subtly regulating where and how new stars form in the galactic core. This kind of gentle, long-term feedback is harder to detect than the dramatic effects seen in active galaxies, but it may be just as important for understanding how galaxies evolve over billions of years. This adds a layer of continuity to the story of black holes. Instead of being exceptional, dramatic objects that only matter in rare, extreme cases, they become ongoing participants in the life of their galaxies, influencing structure and evolution even in their quieter phases. There's also a shift in how scientists think about predictability. In simpler models, the behaviour of material near a black hole could often be described in relatively smooth average terms. Accretion rates, disk temperatures, and radiation outputs could be treated as stable values, with occasional deviations. The frequent small-scale variability observed near Sagittarius A suggests a more stochastic or random component to the system. Instead of smooth flows, there are clumps, bursts, and irregular patterns driven by turbulence and magnetic interactions. This doesn't mean the system is unpredictable in a fundamental sense. It means that to understand it, scientists have to think in terms of statistics and distributions rather than single, neat curves. This kind of thinking is common in fields like weather forecasting or fluid dynamics, where complex systems produce patterns that are only meaningful when considered over long periods and large data sets. Applying this approach to black holes represents a conceptual shift, one that treats their environments as complex, evolving systems rather than simple, steady-state machines. Another important change involves the way black holes are used as tests of fundamental physics. Sagittarius A has long been a valuable laboratory for testing general relativity, especially through the precise tracking of stellar orbits. Those tests have been remarkably successful, confirming the theory's predictions in a regime of strong gravity. The new observations add another layer to this testing. The behaviour of light and matter near the event horizon is influenced not just by gravity, but also by relativistic effects related to motion and space-time curvature. By studying time variations, motion patterns, and the structure of the accretion flow, scientists can test models that combine relativity with magnetism and fluid dynamics. This is a more demanding challenge than testing gravity alone. It requires theories that can handle multiple interacting forces in extreme conditions. Webb's data doesn't just provide a new test case, it provides a detailed, ongoing one where models can be compared to observations across a wide range of timescales and conditions. This helps refine our understanding not just of black holes, but of the fundamental laws that govern the universe. There's also a broader, more philosophical shift that comes from this work. Black holes are often portrayed as places where physics ends, where our theories break down and the unknown begins. That's true in the deepest sense, at the singularity itself, where our current understanding of space and time fails. But the region around the black hole, the part we can observe, is becoming a place where physics is actively explored, tested, and extended. Instead of a boundary to knowledge, the black hole becomes a frontier, a place where familiar principles are pushed to their limits and new insights can emerge. This change in perspective is subtle but meaningful. It transforms the black hole from a symbol of finality into a symbol of ongoing inquiry. There's also an emotional component to this shift, even if it's not often discussed in scientific papers. For many people, black holes evoke a sense of fear or awe, a feeling of something overwhelmingly powerful and unknowable. The detailed, patient observations of Sagittarius A add a layer of familiarity to that image. They don't make the black hole less extreme, but they make its environment more relatable. You can think in terms of flows, fields, and patterns rather than pure abstract gravity. This doesn't diminish the wonder, it changes its tone. Instead of a distant, incomprehensible monster, the black hole becomes part of a larger, more understandable system, one that follows the same basic rules as other parts of the universe, even if those rules are operating in an especially intense way. From a practical standpoint, these changes in understanding influence how future observations are planned. Scientists are now looking for ways to combine data from Webb, the Event Horizon Telescope, X-ray observatories, and radio arrays into a single coordinated picture. Each of these instruments sees a different aspect of the system, and together they can reveal how processes at different scales and energies are connected. This multi-messenger, multi-wavelength approach reflects the new view of black holes as complex multi-layered systems rather than simple, isolated objects. It also means that progress is increasingly collaborative. Understanding Sagittarius A now involves astronomers, physicists, computer scientists and engineers working together, each contributing a piece of the puzzle. Observations feed into simulations. Simulations suggest new observations. The cycle repeats. This kind of work takes time. There are no quick answers, no final conclusions that neatly wrap up the story. Instead, there's a gradual deepening of understanding, a sense that each new detail adds another layer to a picture that will always remain, in some sense, incomplete. From where you are now, listening to this, the idea that our understanding of black holes is changing might feel both distant and strangely relevant. We often carry simple images of complex things, whether they're people, places, or ideas. Over time, as we pay closer attention, those images tend to grow more detailed, more nuanced. We start to see patterns and connections we hadn't noticed before. The story of Sagittarius A is like that on a cosmic scale. What was once a dark, heavy presence at the centre of the galaxy is becoming a richly textured environment, shaped by gravity, magnetism, motion, and time. This doesn't make the black hole less mysterious. It makes the mystery more layered. There are still deep questions about what happens at the event horizon, about the nature of singularities, about how gravity and quantum mechanics might fit together in these extreme conditions. But around those questions, there is now a growing body of knowledge about how black holes live within their galaxies, how they interact with their surroundings, and how they participate in the long, slow evolution of cosmic structures. As Webb and other instruments continue to observe Sagittarius A, this picture will likely continue to evolve. New patterns will be noticed, old assumptions will be tested. The boundaries between what we think we know and what we're still trying to understand will shift again. For now, what stands out most is the sense that black holes are not just endings, they are also beginnings, not in the sense of creating matter or energy, but in the sense of opening up new ways of thinking about how the universe works. They challenge our theories, they inspire new tools, they connect the smallest scales of physics with the largest structures in the cosmos. And in the quiet, patient glow of infrared light from the heart of the Milky Way, they remind us that even the darkest places can be sources of insight if we take the time to look closely enough. When you spend time getting to know a single place in detail, it often starts to change how you think about similar places elsewhere. A familiar street can teach you about the rhythm of an entire city. A single shoreline can give you clues about how oceans shape coastlines around the world. In much the same way, the careful study of Sagittarius A is beginning to reshape how scientists think about the centres of galaxies far beyond the Milky Way. At first glance, our galaxy might seem like a poor stand-in for the universe as a whole. The Milky Way is relatively quiet compared to the blazing, energetic galaxies often featured in astronomical images, the ones with bright cores and long glowing jets stretching out into space. Sagittarius A is not a dramatic, luminous beacon. It doesn't dominate the sky with intense radiation. It doesn't announce itself with powerful outflows visible across millions of light years. And yet, precisely because it is calm, it offers a kind of clarity. In a quieter system, the underlying processes are easier to disentangle. The glare of extreme activity doesn't wash out the subtle details. The environment around the black hole can be studied in layers, from the slow motion of stars to the gentle glow of dust, to the faint flickers of energy in the infrared. This makes Sagittarius A a kind of reference point, a baseline against which more active galactic centres can be compared. One of the first lessons it offers is about scale and continuity. For a long time, astronomers tended to divide galaxies into broad categories. There were active galaxies, with bright, energetic cores powered by rapidly feeding black holes. And there were normal, quiet galaxies, like our own, where the central black hole seemed to play a much smaller role in everyday galactic life. The detailed observations of Sagittarius A suggests that this division may be more of a spectrum than a sharp boundary. The same kinds of processes that dominate in active galaxies, accretion flows, magnetic fields, energy release, and feedback into the surrounding environment, appear to be happening in the Milky Way as well, just at a lower intensity. The flickers of infrared light, the circulating material, and the subtle outflows hint at a scaled-down version of the same engine that powers much more dramatic systems. This continuity implies that galaxies may move along this spectrum over time. A galaxy that is quiet now might have been active in the past. One that is active today may eventually settle into a calmer phase. The difference is not necessarily in the fundamental nature of the black hole or the galaxy, but in the conditions that surround it. How much material is available to feed the black hole, how that material is distributed, and how the galaxy's structure channels it toward the center. Sagittarius A provides a snapshot of one point along this continuum. By studying it in detail, scientists can better understand what a black hole looks like when it is operating in a low-energy turbulent mode. That, in turn, helps them interpret observations of distant galaxies, where similar processes might be happening, but are hidden behind layers of brightness and distance. Another lesson comes from the relationship between black holes and their host galaxies. In more active systems, it's clear that black holes can have a dramatic impact on their surroundings. Powerful outflows and radiation can heat and disperse gas, suppressing star formation across large regions of the galaxy. This kind of feedback can shape the size, structure, and evolution of the galaxy itself. In the Milky Way, the influence of Sagittarius A is much more subtle, but it still appears to be present. The circulation of material near the galactic center, the balance between inflow and outflow, and the way dust and gas are distributed all suggest a quieter form of feedback. Instead of dramatic, galaxy-wide effects, there may be a steady, long-term influence that gently shapes the central region over millions of years. This raises an important point about timescales. Galaxies evolve slowly. The stars we see in the sky live for millions or billions of years. The structures of spiral arms and central bulges change over similarly long periods. The influence of a black hole doesn't have to be immediate or dramatic to be significant. Even a small, consistent effect applied over a long time can reshape the environment in meaningful ways. By watching Sagittarius A in its current state, scientists can begin to piece together how this kind of slow, steady feedback might work. They can look for signs of how material is being mixed, how star formation is being influenced in the central region, and how energy is being distributed through the surrounding gas and dust. These details can then be used to inform models of galaxy evolution more broadly. Another key insight comes from the structure of the environment around Sagittarius A. The circumnuclear disk, the filaments of dust, and the turbulent inner accretion flow all form a layered, interconnected system. Material doesn't move in a straight line from the outskirts of the galaxy to the event horizon. It passes through different regions, each with its own physical conditions and processes. This kind of multi-stage journey is likely common in other galaxies as well. In more active systems, the details may be harder to see, but the same basic structure may be present. Large-scale inflows bring gas toward the center. Dense rings or disks store and redistribute that material. Inner accretion flows feed the black hole and generate energy. By studying these stages in the Milky Way, where they can be observed with relatively high resolution, scientists can build a more complete picture of how material moves through galactic centers in general. There's also a lesson in the role of magnetic fields. Magnetic fields are difficult to observe directly, especially in distant galaxies, but the pattern seen near Sagittarius A suggests that they play a major role in shaping the flow of material and the release of energy. If magnetism is as important in our galaxy as it appears to be, it's likely to be important elsewhere too. This means that models of active galactic nuclei, which often focus heavily on gravity and radiation, may need to give more attention to magnetic processes. The way jets are launched, the way accretion disks form and evolve, and the way energy is transported through the system may all depend strongly on the structure and behaviour of magnetic fields. Sagittarius A offers a nearby laboratory for studying these effects in detail. By observing how filaments align, how energy bursts occur, and how material moves along preferred pathways, scientists can test their ideas about magnetism in a setting where the data is rich and accessible. Those ideas can then be applied to more distant, less resolved systems. Another area where Sagittarius A provides valuable context is in the study of variability. Many active galaxies show dramatic changes in brightness over time. They can flare, fade, and shift in ways that reveal information about the size and structure of their central regions. Interpreting these changes, however, can be challenging when you're looking at a system millions or billions of light years away. The time variations seen near Sagittarius A offer a kind of guide. By understanding how small-scale, low-level variability arises in a quiet system, scientists can develop better tools for interpreting the more dramatic variations seen in active galaxies. They can ask which features are likely to be caused by turbulence, which by magnetic reconnection, and which by changes in the rate at which material is falling into the black hole. This comparative approach helps turn variability from a confusing signal into a meaningful diagnostic. There's also a lesson in the diversity of environments around black holes. Not all galactic centres look the same. Some are dominated by young, massive stars. Others are filled with older stellar populations. Some have dense, well-defined disks of gas and dust. Others are more diffuse. Sagittarius A sits in a region that includes all of these elements. It's crowded with stars of different ages. It's surrounded by complex structures of gas and dust. It's influenced by both gravity and magnetism. This diversity makes it a useful case study for exploring how different components interact. By teasing apart the contributions of stars, gas, dust, and fields in our own galaxy, scientists can develop a more flexible framework for understanding other galaxies, where the balance between these components may be different. Another important insight involves the idea of universality. For a long time, astronomers have looked for universal relationships that connect black holes and galaxies. One of the most famous is the correlation between the mass of a galaxy's central black hole and the properties of its central bulge of stars. This suggests that black holes and galaxies grow together, influencing each other over cosmic time. The detailed study of Sagittarius A adds texture to this idea. It shows how, on a day-to-day basis, that long-term relationship might be maintained. The slow circulation of material, the gentle feedback into the surrounding environment, and the subtle influence on star formation all provide possible mechanisms for how black holes and galaxies stay linked over billions of years. This turns an abstract correlation into a more concrete process. Instead of simply noting that black hole mass and galaxy structure are related, scientists can begin to describe how that relationship is maintained through ongoing, small-scale interactions. There's also a lesson in humility. The Milky Way is our home galaxy. We often use it as a standard, a reference point for understanding the universe. But in many ways, it's not particularly special. It's a fairly typical spiral galaxy with a fairly typical supermassive black hole at its centre. This makes Sagittarius A especially valuable. By studying it in detail, scientists are not just learning about a unique object, they're learning about a class of objects that likely exists in countless galaxies across the universe. The insights gained here can be applied broadly, helping to interpret observations of systems that are too far away to study with the same level of detail. There's also a connection to the history of the universe. The earliest galaxies formed in a very different environment, when the universe was younger, denser, and richer in gas. Their central black holes may have grown rapidly, shaping the galaxies around them in dramatic ways. By understanding how a black hole and its galaxy interact in a quieter, more mature system like the Milky Way, scientists can build a more complete picture of how these relationships evolve over cosmic time. They can ask how the processes seen today might differ in a younger universe, and how those differences might have influenced the growth of the first galaxies and black holes. Another area where Sagittarius A offers perspective is in the study of extremes. Active galactic nuclei can be so bright that they outshine their entire host galaxies. Their jets can stretch across intergalactic space, influencing the environment far beyond the galaxy itself. These are some of the most powerful phenomena in the universe. By contrast, Sagittarius A operates at a much lower level of energy. Studying this quieter end of the spectrum helps scientists understand what black holes look like when they are not in these extreme states. It fills in the lower energy part of the picture, providing a more complete understanding of black hole behavior across all regimes. This is important for building comprehensive theories. A theory that only explains the most dramatic cases is incomplete. To truly understand black holes, scientists need models that can account for both the blazing, active systems and the subtle, quiet ones. Sagittarius A is a key piece of that puzzle. There's also a practical benefit to this work. Future telescopes and observatories will be able to study distant galaxies in greater detail than ever before. They will produce enormous amounts of data, revealing complex structures and variations in light across vast regions of space. Having a well-studied nearby example like the Milky Way center will help scientists make sense of that data. They can use Sagittarius A as a kind of training ground, a place where they can test their analysis techniques, refine their models, and develop their intuition about what different patterns of light and motion might mean. This preparation will be invaluable as new instruments open up even more of the universe to detailed observation. There's also an interesting psychological aspect to all of this. It's often easier to feel connected to something that feels familiar. The idea that the same kinds of processes happening at the heart of the Milky Way are also happening in galaxies millions or billions of light years away creates a sense of continuity. It suggests that despite the vastness of the universe, there are common patterns, shared structures, and repeating themes. The black hole at the center of our galaxy becomes a kind of bridge, linking our local cosmic neighborhood to the broader universe. By understanding it, we gain a way to think about distant galaxies not as completely alien places, but as systems shaped by the same basic forces and processes. There's a quiet comfort in that idea, not because it makes the universe smaller, but because it makes it more coherent. From where you are now, the notion that a single black hole can teach us about countless galaxies might feel like a leap. But in science, that's often how understanding grows. You study one thing in detail, you identify patterns and processes, you look for those same patterns elsewhere. Over time, a broader picture emerges. Sagittarius A is becoming one of those anchor points, a place where detailed, careful observation meets broad, far-reaching theory. As the data continues to accumulate, the lessons it offers are likely to expand. New connections may be drawn between the Milky Way and distant galaxies. New models may emerge that better explain how black holes and galaxies co-evolve. New questions may arise about the role of environment, history, and chance in shaping these systems. This process doesn't move quickly. It unfolds over years, even decades, as observations are refined, models are tested, and ideas are debated. But each step adds a little more clarity to the picture of how the universe organizes itself on the largest scales. In the end, what Sagittarius A teaches us about other galaxies is not just a set of technical details about accretion flows or magnetic fields. It offers a way of thinking about the universe as a connected whole, where the behavior of a single object can illuminate the nature of many others. It reminds us that, even in the vastness of space, patterns repeat, processes echo, and understanding gained in one place can resonate far beyond its point of origin. And as that understanding deepens, it naturally invites a broader reflection, one that steps back from the mechanics of galaxies and black holes and turns toward a more personal question. If the same forces and patterns that shape the heart of the Milky Way are at work across the universe, what does that say about our own place within it, and how we fit into this long, interconnected story of matter, energy, and time that stretches across billions of years and countless stars? There's a subtle shift that happens when you move from thinking about what something is to thinking about what it means. The first question invites description, measurement, and explanation. The second invites reflection, connection, and a different kind of attention. As the observations of Sagittarius A and the work of telescopes like Webb begin to settle into a broader understanding of black holes and galaxies, that second kind of question naturally comes forward. Not in a philosophical, abstract sense, but in a grounded, almost practical way. What does all of this tell us about space, about time, and about where we find ourselves within the vast structure that these ideas describe? Space, for most of human history, was treated as a simple backdrop. It was the stage on which the stars and planets moved, a kind of empty container that held everything else. Even as astronomy advanced, that image lingered. Space was where things were, but it wasn't something in its own right. The region around Sagittarius A challenges that idea in a very direct way. Near a black hole, space itself is shaped and stretched. The paths that objects and light follow are not just determined by where they start and how fast they move, but by how the space between points is curved. The environment that Webb and other instruments are observing is not simply a collection of objects floating in emptiness. It is a structure where the geometry of space plays an active role in shaping what happens. This changes how scientists talk about distance and position. When light travels from the galactic center to Earth, it doesn't move along a straight, simple line in a flat, unchanging space. It follows a path through a landscape that has been shaped by the massive stars, clouds of gas, and the black hole itself. The fact that we can reconstruct what's happening there, from subtle shifts in infrared light, is a reminder that space is not passive. It participates in the story. Time, in a similar way, stops being just a clock that ticks uniformly in the background. In everyday life, time feels steady and reliable. A second is a second, a minute is a minute, and those units don't seem to depend on where you are or how you're moving. But near Sagittarius A, time behaves differently. The stronger the gravity, the more time slows down relative to regions farther away. This is not a theoretical idea. It's a measured effect, one that has been confirmed in experiments much closer to home, like the way clocks on satellites tick slightly faster than clocks on the ground. Near a black hole, this effect becomes much more pronounced. While Webb's observations don't directly show time slowing down, the motions and variations they capture are shaped by an environment where the flow of time itself is not uniform. The orbits of stars, the movement of gas, and the paths of light are all influenced by this distortion. This introduces a different way of thinking about what it means to observe something. When you look at Sagittarius A, you're not just seeing a place far away, you're seeing a place where time has been running at a different pace than it does for you. The light arriving at the telescope carries information from a region where the fundamental relationship between space and time is different from what you experience in your daily life. That realization can feel distant and technical, but it also has a quiet, grounding quality. It suggests that the universe is not built on a single, universal clock or a single, fixed grid of space. It's built on a flexible structure, one that adapts and responds to the presence of matter and energy. From that perspective, our own position in the universe takes on a slightly different character. We often think of ourselves as observers looking out at a vast external world. But the physics that shapes the galactic center also shapes the space and time around us, just on a much gentler scale. The same principles that bend light near a black hole also determine how GPS satellites work. The same interplay between mass and space-time that governs the orbits of stars around Sagittarius A also governs the path of the Moon around the Earth. The difference is not in the rules, it's in the intensity with which those rules are expressed. This connection between the extreme and the familiar is one of the quieter outcomes of studying places like the galactic center. It turns abstract concepts into something more continuous with everyday experience. Space and time are not distant. cosmic ideas that only matter near black holes or at the edge of the universe. They are the framework within which every movement, every change, and every moment of experience takes place. Another aspect of this work that touches on our place in the universe is the idea of scale. The Milky Way is about 100,000 light-years across. Sagittarius A sits near its centre, 26,000 light-years from Earth. Webb's observations allow scientists to study structures that are measured in fractions of a light-year within that region, and variations that occur over minutes or hours. These numbers can be hard to hold in your mind all at once. They span distances and timescales far beyond anything we encounter in daily life. And yet, they are all connected in a single continuous system. The movement of a dust grain near the black hole, the orbit of a star in the galactic core, the rotation of the Milky Way's spiral arms, and the expansion of the universe itself are all part of a nested set of processes, each one influencing and influenced by the others. This layered structure gives a sense of depth to the idea of place. You're not just on a planet orbiting a star. You're in a solar system moving through a galaxy, in a galaxy moving through a group of galaxies, in a universe that has been expanding for nearly 14 billion years. The study of Sagittarius A makes this nesting more tangible. By focusing on a specific extreme location within our own galaxy, scientists can trace how local processes connect to larger patterns. The flow of material around the black hole is influenced by the structure of the galaxy. The galaxy's structure is influenced by its history of star formation and mergers. That history is influenced by the broader environment of the universe as a whole. This chain of connections runs in both directions. The central black hole doesn't just respond to the galaxy, it also helps shape it, through feedback processes that influence how gas and stars are distributed in the core. Over long periods, this can affect the overall appearance and evolution of the Milky Way. In that sense, the place where you are on a planet far out in one of the galaxy's spiral arms is linked, indirectly but genuinely, to what happens near the black hole at the centre. Another way these observations influence our sense of place is through the idea of time as a record. The light Webb collects from the galactic centre left that region tens of thousands of years ago. When you think about that, it becomes clear that every astronomical observation is also a look into the past. You're not seeing Sagittarius A as it is right now. You're seeing it as it was when early humans were beginning to spread across the Earth, when ice sheets still covered large parts of the planet. This adds a temporal dimension to the idea of place. The universe is not just a spatial structure. It's a historical one. Every region you look at is also a moment in time frozen in light. This perspective can make the universe feel both larger and more intimate at the same time. Larger, because it reminds you that the cosmos has a deep history, stretching back billions of years before you were here and continuing long after. More intimate, because the light you receive now is the result of events that happened in a specific place, at a specific time, and have been travelling ever since to reach you. The study of black holes and their environments also touches on a more subtle aspect of our place in the universe, which is the relationship between the known and the unknown. Black holes represent one of the boundaries of current understanding. At the event horizon, our theories begin to break down. We can describe what happens outside with great precision, but what happens inside remains for now beyond direct observation and full theoretical clarity. This creates a kind of horizon in our knowledge, not unlike the physical horizon around the black hole itself. Working near that boundary, as scientists do when they study Sagittarius A, highlights how much of the universe is both understood and not yet understood. This doesn't diminish what we know, it frames it. Every new observation, every refined model, pushes that boundary a little farther. The unknown doesn't disappear, it shifts. There's something quietly reassuring in that process. It suggests that the universe is not a puzzle that will one day be completely solved and then set aside. It's an ongoing project, one where each answer leads to new questions, and where understanding deepens over time rather than reaching a final state. From a more human perspective, this has an interesting parallel. We often think of our own lives in terms of milestones and conclusions, goals reached, problems solved. But much of experience is more like an ongoing process, a series of adjustments and refinements rather than a march toward a single endpoint. The way science approaches something as complex as a black hole, through gradual, careful accumulation of knowledge, reflects that same pattern. Another way the study of space and time around Sagittarius A influences our sense of place is through the idea of connection. It's easy to think of the universe as a collection of isolated objects, stars here, galaxies there, separated by vast distances. But the physics that governs the galactic center also governs what happens on Earth. The atoms in your body were formed in stars. The heavy elements that make up rocks, oceans and living organisms were created in stellar explosions long before the solar system existed. The light you see in the night sky is part of a continuous flow of energy that links distant regions of space to your own eyes. In that sense, studying a black hole is not just about something far away, it's about understanding the broader system that you are already part of. There's also a subtle shift in how time is experienced when you think about cosmic scales. On a human level, time is often measured in years, decades, or, at most, centuries. On a galactic level, meaningful changes can take millions or billions of years. The activity around Sagittarius A that Webb observes, the flickers and flows of material, are happening on timescales that are short compared to the life of the galaxy, but long compared to a human lifespan. This places human experience in a kind of middle ground. You live in a moment that is brief compared to the age of the universe, but long enough to notice patterns, to build knowledge, and to pass that knowledge on. The study of the galactic center is one of the ways that knowledge accumulates across generations. The people who first suggested that a black hole might exist at the center of the Milky Way did not have the tools to observe it directly. The people who track the orbits of stars around an invisible mass built on those ideas. The people who designed and launched Webb extended that work further. Each step is part of a longer timeline of understanding. Thinking about it that way, your own moment of listening to or reading about these observations becomes part of that same chain. You're connected, in a small but real way, to a process that stretches across decades of research and across the vast distances of the galaxy. There's also an interesting tension between the abstract nature of concepts like spacetime and the very concrete way they're studied. On one hand, spacetime is a mathematical idea, described by equations and models. On the other hand, its effects are observed in very practical ways, in the bending of light, in the timing of signals, in the motion of stars. This combination of abstraction and observation is one of the strengths of modern science. It allows ideas that begin as theoretical constructs to be tested and refined through real data. The environment around Sagittarius A is one of the places where this process is happening, in a particularly vivid way. The bending of light, the shifts in time, and the patterns of motion all provide opportunities to test theories of gravity and space-time under conditions that can't be replicated on Earth. This makes the galactic center not just an object of curiosity, but a kind of natural laboratory for exploring the fundamental structure of reality. From a more reflective angle, there's something quietly centering about the idea that the same laws of physics apply everywhere. The rules that govern the behavior of a black hole at the center of the Milky Way are the same rules that govern the motion of a ball rolling across the floor or the flow of electricity through a wire. This universality creates a sense of coherence. The universe is not a patchwork of different systems with different rules. It's a single, connected structure where the same principles operate at every scale, from the smallest particles to the largest galaxies. The study of extreme places like Sagittarius A highlights this coherence by showing those principles in their most intense form. There's also a quieter, more personal aspect to this. Looking out at the night sky, or thinking about the center of the galaxy, can evoke a sense of smallness. The distances and times involved are so vast that individual human lives can seem insignificant by comparison. But there's another way to see it. The fact that a species on a small planet can build instruments, develop theories, and understand what's happening near a black hole tens of thousands of light years away is, in its own way, a remarkable connection. It suggests that the universe is not just something we exist within, it's something we can, at least partially, comprehend. This doesn't make us central or special in a cosmic sense. It places us within a broader context of exploration and understanding. Another implication of this work is how it shapes our expectations for the future. As technology advances, our ability to observe and analyze the universe will continue to improve. The questions that are now at the edge of understanding about the nature of space-time, about the behavior of matter near a black hole, about the connection between galaxies and their central engines, may become more approachable. This creates a sense of open-endedness. The story of space and time is not finished. It's being written, observation by observation, model by model, generation by generation. Sagittarius A is one chapter in that story, but it's not the last. From where you are now, thinking about space, time, and place in this way can feel both expansive and grounding. Expansive, because it opens up a view of the universe as a vast interconnected system, shaped by forces that operate across unimaginable scales. Grounding, because it ties those forces back to familiar ideas, like motion, energy, and change. There's a quiet continuity between the everyday and the cosmic. The same patterns of cause and effect, of interaction and response that you see in the simple systems, are present in the most extreme environments in the universe. As the observations of Sagittarius A continue to be analysed and interpreted, this sense of continuity is likely to deepen. New details will emerge, new connections will be made. The picture of how space and time work and how we fit within them will become more refined, but it will not become final. There will always be edges to our understanding, places where questions remain open and ideas are still forming. That, in a way, is part of what gives this whole exploration its quiet appeal. It's not a journey toward a single definitive answer. It's an ongoing process of noticing, connecting, and rethinking. There's a particular feeling that comes when your attention slowly returns from something far away. Not a sudden snap back to the present, but a gentle easing, like letting your eyes adjust after looking at a distant horizon for a long time. That's a natural place to settle when thinking about the long path we've followed, from the crowded, energetic region around Sagittarius A back to the quiet space where you are right now. For most of this journey, the focus has been on things that exist at a scale that's difficult to hold in your mind all at once. A black hole with a mass millions of times greater than the Sun, stars moving at speeds that make even the fastest spacecraft seem slow, light that has been travelling for tens of thousands of years just to reach a telescope, and then a little longer to reach your awareness. And yet, here you are, in a room, on a planet, in a moment that feels small and familiar. The connection between those two perspectives, the cosmic and the everyday, is not as thin as it might seem. When you think about Sagittarius A, it's easy to imagine it as something completely separate from your own experience, an object so distant and extreme that it has no real bearing on your life. But the same physical rules that shape the environment around that black hole also shape what's happening in the quiet space around you now. Gravity holds you to the ground. Electromagnetism keeps the atoms in your body together. Light from nearby lamps or distant stars enters your eyes and becomes part of how you see the world. Time moves forward, one moment after another, at a pace that feels steady and familiar. The difference between your world and the world near the centre of the galaxy is not in the rules, it's in the intensity. The Milky Way's core is a place where those rules are expressed with extraordinary force. Gravity bends space more noticeably. Motion reaches extreme speeds. Energy is released in ways that are difficult to replicate anywhere else. But at a fundamental level, it's still the same universe, operating under the same principles. That continuity is part of what makes the night sky feel both distant and close at the same time. If you happen to be somewhere you can see the stars, even a few of them, there's a quiet reminder in that view. The light you're seeing left those stars long ago. It crossed vast distances, passed through clouds of gas and dust, slipped through the subtle curvature of space shaped by countless masses along the way, and finally reached you. In a very literal sense, the universe is always arriving. The study of Sagittarius A adds another layer to that idea. The infrared light Webb collects from the galactic centre is part of that same flow. It's just tuned to a different part of the spectrum, a different way of seeing the same underlying reality. When scientists analyse that light, they're not just learning about a black hole, they're learning about how space, time and matter interact everywhere. There's something quietly grounding in realising that the universe is not divided into separate, disconnected regions, each with its own set of rules. It's a single, continuous system, one where events in one place can, in subtle ways, be connected to conditions in another. That doesn't mean what happens near Sagittarius A has a direct, immediate effect on your day-to-day life. The distances are too great for that kind of cause and effect. But it does mean that you are part of the same overall structure, subject to the same underlying patterns. From a broader view, the Milky Way itself is a kind of bridge between the cosmic and the familiar. It's large enough to contain billions of stars, vast clouds of gas, and a supermassive black hole at its centre. But it's also the home of your own solar system, your own planet, and the particular patch of sky you can see from wherever you are now. When you look up, you're not just seeing the universe in an abstract sense. You're seeing your galaxy from the inside. The bright band of the Milky Way, if you can see it, is a view across the disk of the galaxy, through countless stars and clouds of dust. Somewhere in that band, in the direction of the constellation Sagittarius, lies the region where Sagittarius A sits, hidden behind thick layers of interstellar material. You can't see the black hole itself. You can't even see the stars closest to it with your eyes, but you can see the broader structure that it's part of, the spiral arms, the glowing haze of distant suns, the subtle variations in brightness that hint at depth and distance. There's a quiet continuity in that view. The same galaxy that contains a supermassive black hole at its heart also contains the star that your planet orbits, the Sun, and the familiar patterns of constellations that people have been noticing and naming for thousands of years. Those patterns have changed slowly over time as stars move and as the Earth's axis shifts, but the act of looking up has remained much the same. The difference now is that, in addition to seeing the stars, we also have a growing understanding of what lies behind them, around them, and between them. That understanding doesn't replace the simple experience of looking at the sky. It adds a layer to it. You can look up and see a few points of light. You can also, if you choose, think about the fact that those points of light are part of a galaxy that has a complex active core, shaped by a black hole, magnetic fields, and the slow circulation of matter. Both perspectives can exist at the same time. There's also something quietly human about the way this knowledge has been built. The idea that there might be a massive invisible object at the centre of the Milky Way was, for a long time, just a hypothesis. It was based on indirect clues, on the way stars moved, on the way radio waves were emitted from a compact region in the sky. Over decades, those clues were followed up with better instruments, more precise measurements, and more refined theories. The picture gradually became clearer. The James Webb Space Telescope is one of the latest steps in that process. It didn't appear out of nowhere. It's the result of years of planning, engineering and collaboration, of people working together across countries and generations to build something that could extend human senses into a part of the universe we can't reach ourselves. When Webb sends back data, it's easy to focus on the images and the science. But behind those are countless individual efforts, from the design of the mirror segments to the writing of the software that processes the data, to the analysis carried out by scientists around the world. That collective effort is part of the story too. It's a reminder that our understanding of the universe is not the product of a single moment or a single mind. It's a shared, ongoing project, one that builds slowly over time. From a more personal angle, there's something quietly reassuring in the idea that even as the universe operates on scales far beyond everyday experience, there's room for human curiosity and attention within it. You don't need to be an astronomer or a physicist to feel a connection to the night sky. You just need to notice it. There's a simple, almost meditative quality to that act, standing or sitting somewhere quiet, letting your eyes adjust to the darkness, watching as a few stars become many, noticing the slow movement of a satellite or the brief streak of a meteor. These are small, gentle experiences, but they're also points of contact with a much larger reality. The knowledge that there's a supermassive black hole at the centre of the galaxy doesn't have to make the sky feel more intimidating. It can make it feel more layered, more interesting, more full of stories that stretch beyond what you can see. There's also an interesting shift that happens when you think about time in this context. The light from Sagittarius A that Webb observes left that region tens of thousands of years ago. The light from the stars you see in the sky left them anywhere from a few years to thousands of years ago, depending on how far away they are. That means that when you look up, you're not seeing the universe as it is right now. You're seeing a collection of moments from the past, arriving together in the present. This doesn't usually change how the sky looks to you. The stars still appear steady and constant. But it adds a layer of depth to the experience. Each point of light carries a little piece of history. In that sense, the night sky is not just a view, it's a record. The study of the galactic centre extends that idea further. By observing changes in the infrared light over time, scientists are building a kind of timeline for a place far away, a record of how energy and matter move through one of the most extreme environments in the galaxy. This timeline, in turn, becomes part of a much larger story about how the Milky Way has evolved over billions of years, how stars have formed and died, how gas has flowed and been reshaped, and how the central black hole has grown and changed. Your own life, in comparison, might feel brief, but it's also part of that same unfolding history. The atoms in your body were forged in stars that lived and died long before the sun was born. The planet you're on formed from the remnants of earlier generations of stars. The light you see in the sky is part of an ongoing exchange of energy that connects different parts of the galaxy and the universe beyond it. Thinking about it that way can make the idea of place feel broader. You're not just in a room, in a city, on a planet. You're in a galaxy, in a universe, in a long chain of events that stretches back to the earliest moments after the Big Bang. That doesn't mean you have to carry all of that in your mind all the time. It just means that when you choose to, you can let your perspective widen a little. There's also a quieter, more immediate aspect to drifting back to Earth. After thinking about black holes, magnetic fields, and the structure of space-time, the simple details of your surroundings can take on a slightly different tone. The sound of your own breathing, the feel of the surface you're sitting or lying on, the subtle changes in light and shadow in the room. These are small, familiar things, but they're also part of the same physical universe. The air you breathe is a mixture of gases shaped by the chemistry of Earth's atmosphere, which in turn is influenced by the sun's energy, which comes from nuclear reactions in the sun's core, which involve the same fundamental forces that operate in stars across the galaxy. There's a chain of connections there, from the cosmic to the immediate. You don't need to trace that chain in detail to appreciate it. Just noticing that it exists can be enough. In a way, the journey from Sagittarius A back to a quiet night sky is also a journey from complexity to simplicity. The environment around the black hole is filled with tangled forces, extreme conditions, and interactions that challenge our best theories. The night sky, as you see it, can be just a few points of light against a dark background. Both views are true, they're just different layers of the same reality. There's something gently balancing about holding those layers together. You can be aware of the vast, intricate structure of the galaxy and still appreciate the simple beauty of a clear night. Another thought that often comes up in this context is the idea of direction. In everyday life, we think in terms of up and down, north and south, left and right. In space, those directions lose much of their meaning. There's no absolute up in the universe. Everything is moving relative to everything else. The Milky Way is rotating. The solar system is moving through the galaxy. The galaxy is moving within a group of galaxies. That group is moving within the larger structure of the universe. From that perspective, the idea of drifting back to Earth is more about attention than about actual movement. You're not really moving through space when you shift your focus from the galactic center to your own surroundings. You're just changing the scale at which you're paying attention. That's something you can do at any time. You can think about the smallest details of your immediate environment, or you can think about the largest structures in the universe. Both are part of the same continuum. There's a kind of quiet freedom in that. It means you don't have to choose between the cosmic and the personal. You can move back and forth between them, letting one inform the other. The study of Sagittarius A can make the night sky feel deeper and more layered. The experience of a quiet night can make the science feel more grounded and real. Another subtle effect of this kind of reflection is how it can change your sense of time. Thinking about events that unfold over millions or billions of years can make everyday concerns feel smaller, or at least differently sized. That doesn't make them unimportant, it just places them in a broader context. In that broader context, a moment of quiet attention, a few minutes spent looking at the sky or thinking about distant places, can feel like a small pause in a very long story. There's something gently comforting about that idea. The universe has been here for a long time. It will be here for a long time to come. Your moment within it is brief, but it's also uniquely yours. The light from Sagittarius A and from distant stars will continue to travel through space, whether or not anyone is there to observe it. But when you do take a moment to notice it, to think about where it comes from and what it represents, you're adding a human layer to that ongoing process. You're turning a flow of energy into a story, a set of ideas, a sense of connection. There's also a practical side to all of this. The research being done on black holes, galaxies, and the structure of space-time doesn't just stay in the realm of astronomy. It influences technology, mathematics, and our general understanding of how complex systems work. The same kinds of models used to study turbulence near a black hole can inform studies of fluid dynamics on Earth. The techniques developed to process and analyze astronomical data can be applied in other fields that deal with large, complex data sets. In that sense, the work done to understand a distant, invisible object at the center of the galaxy can have ripple effects that reach much closer to home. But even if you set aside all of those practical connections, there's still something quietly valuable about simply knowing a little more about where you are in the universe. Not in a precise technical sense, but in a broader, more reflective way. Knowing that the galaxy has a heart. Knowing that that heart is active, dynamic, and complex. Knowing that the light from that region can reach us, be collected by a telescope, and be turned into knowledge. Those are small pieces of a very large picture. As the attention drifts back from the galactic center to the night sky, and from the night sky to the room you're in, there's a chance to hold both views at once. The idea of a black hole shaping the core of a galaxy. The simple reality of being here, now, in this moment. Neither one cancels out the other. They coexist. The universe is vast and intricate. Your experience of it is immediate and personal. Both are part of the same story, and that story doesn't really have a final page. New observations will be made. New ideas will be developed. The picture of Sagittarius A and of the universe as a whole will continue to change and deepen. From time to time, you might look up at the sky and remember that there's a place, far beyond what you can see, where gravity, magnetism, and motion come together in an extreme and fascinating way. You might also notice the quiet around you, the steady rhythm of your own breathing, the simple presence of being here. Those two awarenesses, the cosmic and the immediate, can sit side by side without competing. In that balance, there's a kind of calm, not because everything is understood or settled, but because there's room for both curiosity and rest, for both the vast questions of space and time and the simple, grounding experience of a quiet night. As the universe continues its long, patient unfolding, and as instruments like Webb continue to extend our view into its deeper and darker regions, there will always be another layer to explore, another pattern to notice, another connection to make. For now, though, it can be enough to let the focus settle back where you are, beneath whatever sky you happen to be under, carrying with you the idea that somewhere out there, at the heart of your galaxy, there is a place of constant motion and subtle light, quietly shaping a story that you are, in your own small way, a part of.